Have you ever wondered what lies in the deepest, darkest corners of space? For so long, we have pictured black holes as the final word in the cosmic story, a place where everything ends. But what if the universe has imagined something different? What if, at the very edge of collapse, a star could find a way to hold itself in perfect, eternal balance? Tonight, we will wander through this gentle possibility together. But first, allow yourself to settle in. Find that comfortable position in your bed, where your body feels heavy and supported. Let the day's thoughts soften and drift away, like clouds passing by a silent moon. As you begin to relax, I'd love to know where you are joining me from on this journey. If you feel inclined, you can share your city or country and the time of your evening in the comments below. For now, simply be here and breathe. We begin our journey tonight in a place that feels familiar, a place of profound quiet in the cosmic ocean. Here, in the gentle darkness, we will reacquaint ourselves with an old and silent wonder, the foundation upon which our new story will be built. Let your mind drift now, out past the planets and the bright, bustling stars of our galaxy. Travel further, into the deep and quiet spaces between the arms of the Milky Way, into a vast and silent sea of stillness. It is here that we encounter the most profound objects of our known universe, black holes. For a long time, we have spoken of them with a sense of fear or aggression, calling them monsters or cosmic vacuum cleaners. But tonight, let us see them differently. Let us see them not as voids, but as presences. Imagine a black hole as a perfectly smooth dark sphere, hanging motionless in the velvet black of space. It does not hunt. It does not chase. It simply is. It is an ancient feature of the cosmos, as old as the galaxies themselves, a place where the universe has gathered an immense amount of mass into a single, quiet point. Think of it like the deepest part of an ocean. In the ocean, currents flow and life moves. But in the deepest trenches, there is a profound calm, a heavy stillness where the weight of the water above creates a place of serene, unchanging peace. A black hole is like that, but for space-time itself. It is a place where gravity has become so concentrated that it creates a well of immense depth. All around it, the fabric of the universe flows. Stars drift by on their billion-year journeys, and galaxies turn in a slow, cosmic dance. But here, at the edge of the black hole, everything slows down. Time itself, like a river approaching a great placid lake, begins to lose its urgency. These objects are the natural endpoint for the most massive of stars. Imagine a star, many times larger than our own sun, burning brightly for millions of years. It lives a brilliant life, fusing elements in its core, shining with a light that travels across galaxies. But all stars eventually run out of fuel. When this colossal star can no longer push back against its own immense gravity, it begins to collapse. The outer layers are thrown off in a spectacular explosion, a supernova that for a brief moment can outshine its entire galaxy. But the core, the very heart of the star, continues to fall inward, compressing under its own weight, becoming smaller and denser and quieter. This collapse continues, past the density of any material we could ever imagine, until it becomes so compact that it wraps space-time around itself, creating this serene, dark sphere. From a distance, it is almost invisible. It does not shine. It only reveals itself by what it obscures. The stars behind it seem to bend their light around its edges, a gentle and silent distortion in our view of the cosmos. It is a silhouette against the grand tapestry of the universe. When clouds of gas or a wandering star drift too close, they do not fall in with a crash. Instead, they are drawn into a slow, graceful spiral, forming a disk of material that glows brightly as it orbits. This accretion disk is not a sign of violence, but of a cosmic process, a slow and patient merging of matter into a greater whole. It is a quiet, cosmic lighthouse, signaling the presence of a deep and tranquil darkness. Let us hold this image in our minds. Not a monster, but a monument. A silent, patient, and profoundly still presence in the great sea of the universe. waiting peacefully as the cosmos unfolds around it. Flowing from this image of a serene and still presence, let us now gently explore the force that defines it, the very essence of its being: gravity. We feel gravity every moment of our lives. It is the gentle force that holds us to the earth, the quiet tether that keeps the moon in orbit around us, and the sun at the center of our solar system. It is a familiar, comforting presence. Albert Einstein, in a moment of profound insight, imagined gravity not as a force that pulls, but as a curve in the very fabric of the universe, the fabric we call space-time. Imagine a large, soft, flat sheet, stretched out perfectly smooth. This sheet represents our universe. If you place a small pebble on this sheet, it makes a tiny, almost imperceptible dip. This is the gravity of a small object, like a planet. Its influence is local, gentle. Now, imagine placing a heavy bowling ball in the center of the sheet. The fabric sags deeply under its weight, creating a significant curve. This is the gravity of a star. Any smaller marbles rolling nearby will naturally follow this curve, circling the bowling ball in a smooth orbit. They are not being pulled. They are simply following the path of least resistance along the curved surface. This is the nature of gravity. It is the geometry of the universe, shaped by the presence of mass and energy. The more mass you gather in one place, the deeper the curve you create in space-time. A star creates a gentle well. A neutron star, the dense remnant of a smaller star's explosion, creates a much steeper well. Now, imagine something so incredibly dense, so unimaginably massive, that when you place it on our cosmic sheet, it doesn't just create a deep well. It punctures it. It creates a well so deep, so steep, that its sides become vertical. This is what happens at a black hole. The inward pull of the void is simply the consequence of this extreme geometry. It is a slope so profound that, once you cross a certain point, the path of least resistance is no longer a gentle orbit, but a continuous, unceasing journey inward. It is like a river that flows gently for miles, but then reaches a waterfall. Before the edge of the falls, the water can still swirl and eddy, but once it crosses that brink, its path is set. It can only flow downward. The pull of a black hole is just this, the inevitable flow of space-time itself, pouring into the well that the object has created. This gravitational pull extends infinitely far, but it also weakens with distance, just like the light from a candle. Far away from a black hole, its gravity is no different from that of a star of the same mass. If our sun were to magically be replaced by a black hole of the same mass, the Earth and all the other planets would not be sucked in. They would continue in their same peaceful orbits, circling a point of darkness instead of a point of light. The danger, if one can call it that, is not in its reach, but in its proximity. The closer you get, the steeper the slope of space-time becomes. Imagine walking on a gentle hill. You can easily walk around it, change your direction. Now imagine walking near the edge of a deep canyon. The ground becomes steeper, your footing less sure. You have to expend more and more energy to keep from sliding down. Near a black hole, the ground of space-time becomes so steep that eventually, no amount of energy, not even the speed of light, is enough to climb back out. This is the essence of its pull. It is not a hungry force, but a simple, profound, and inescapable consequence of the shape of the universe in its presence. It is a testament to the power of mass to whisper its presence across space-time, gently bending the paths of everything that drifts by. Having understood this deep and peaceful pull of gravity, this profound curvature of space-time, we now drift closer to the black hole itself, towards its most famous and most gently misunderstood feature, the event horizon. The name itself can sound dramatic, like a grand and final boundary, but in reality, if you were to drift towards it in a spaceship, you would not see a line in the sky. There would be no wall, no shimmering curtain, no signpost that says point of no return. The event horizon is a perfectly invisible, perfectly tranquil threshold. Let us return to our analogy of a river flowing towards a great waterfall. Far upstream, the water is calm, and you can easily paddle your boat to either shore. As you drift closer to the falls, the current becomes stronger. You have to paddle harder to move sideways, and eventually, you reach a point where the current is moving faster than you can paddle. At this point, no matter how hard you try, your fate is tied to the flow of the water. You will be carried over the edge. The event horizon is precisely this point, but for space-time instead of water. It is the location around a black hole, where the inward flow of space itself becomes faster than the speed of light. Since nothing in the universe can travel faster than light, once this boundary is crossed, the journey inward is inevitable. It is not a violent capture, but a change in the nature of reality itself. Before you cross the event horizon, you can turn your ship around and fly away, as long as you have enough energy. You have a choice, but once you pass through that invisible gate, all possible paths, every direction you could point your ship, lead towards the center. The future itself has been pointed in a single direction. Space and time trade their familiar roles. The direction inward, toward the center, becomes as inevitable as the direction forward in time is for us now. From the outside, looking in, the event horizon holds a different kind of quiet wonder. As an object approaches it, something strange happens to our perception of its time. Because of the extreme gravity, time for the falling object slows down relative to us, the distant observers. If a friend were waving to you from their ship as they approached the horizon, their wave would appear to go slower and slower and slower. The light from their ship would become redder and dimmer, stretched out by the immense gravity. From our perspective, we would never actually see them cross the boundary. We would see their image frozen, fading over an infinite amount of time, a permanent, silent echo at the edge of the void. The event horizon, then, is not a physical surface you could touch. It is a boundary in space-time, a place where the future narrows to a single path. It is a silent, invisible sphere that encloses a region of the universe from which no story can ever return. It is an embrace from which there is no escape, not because of a force, but because the very fabric of reality allows for no other path. It is the quietest and most absolute farewell in the cosmos. Now, let us contemplate for a moment, from a place of deep relaxation, what it means for something to cross this gentle, invisible boundary. We have seen how, from the outside, an object appears to freeze and fade forever. But what would the journey be like for the object itself? For the traveler crossing the event horizon, nothing special would happen at that exact moment. There would be no bump, no flash of light. One moment, escape is possible. The next, it is not. The transition would be seamless, peaceful. The journey beyond that point, however, is a journey into a place unlike any other. Having passed the event horizon's embrace, the traveler is now fully within the black hole's domain. The universe they left behind is now forever in their past. No message, no light, no signal of any kind can ever travel back out to that universe. The connection has been severed in the most profound way imaginable. It is a one-way journey into the heart of gravity. Inside the event horizon, the pull towards the center becomes overwhelming. The force of gravity is so extreme, and it changes so rapidly over such a short distance, that it begins to exert a differential pull. The part of the traveler's ship closest to the center is pulled more strongly than the part that is farther away. This gentle stretching force, known as the tidal force, would begin to elongate the ship and everything in it, like a piece of clay being stretched. This process is sometimes poetically called spaghettification. For a small, stellar mass black hole, this stretching would begin even before the horizon is crossed. But for a supermassive black hole, 1 millions or billions of times the mass of our Sun, the gravity at the horizon is much gentler, and a traveler could pass through without noticing a thing, the intense stretching only beginning much later on their inward journey. This journey is a journey without end, in a sense. It is a path that leads inexorably towards the center, towards the final mystery of the black hole. The traveler is now disconnected from our observable universe, a silent passenger on the inward-flowing river of space-time. Their story continues, but it is a story that we, on the outside, can never read. It becomes part of the black hole's own quiet history, a piece of information added to the immense collection held within that silent sphere. It is a peaceful passage, a transition from one state of being to another, a merging with the deep gravitational heart of the cosmos. Having contemplated the journey of a single object, let us now zoom out and observe how these silent, massive objects grow and interact with their cosmic environment. This process is often called accretion, and while the term star eater can sound violent, the process is more like a slow, patient merging, a cosmic dance of gravity and matter. A black hole does not actively hunt. It sits in its corner of the galaxy, a silent well of gravity, and simply waits. The universe, in its constant motion, occasionally brings things to it. Imagine a vast, thin cloud of interstellar gas and dust, drifting through the galaxy over millions of years. If its path happens to carry it near a black hole, it will be gently drawn in by the familiar curve of space-time. As this cloud gets closer, it doesn't fall straight in. Instead, because of its own slight rotation, it begins to spiral around the black hole, much like water spiraling down a drain. This spiraling matter flattens into a wide, thin disk, known as an accretion disk. This disk is where the true spectacle happens. The gas and dust within the disk orbit the black hole at incredible speeds. The inner parts of the disk move much faster than the outer parts, and this difference in speed creates friction. The particles of gas and dust rub against each other, and this friction generates an immense amount of heat. The accretion disk can become so hot that it glows brighter than entire galaxies, shining with incredible intensity in X-rays and other forms of light. This is how we often see black holes. We don't see the object itself, but the brilliant, radiant halo of matter that is slowly, gracefully, making its final journey inward. It is a process of transformation. The cool, diffuse gas of interstellar space is transformed into a blazing plasma, its energy released as light before its matter finally crosses the event horizon. This light can tell us a great deal about the black hole, such as its mass and how fast it is spinning. From our distant vantage point, we are witnessing the final luminous sigh of matter before it merges with the black hole and becomes part of its silent mass. Sometimes, it is not just gas, but an entire star that wanders too close. If a star's orbit brings it within a certain distance of a massive black hole, the tidal forces, the same stretching forces we imagined earlier, can be stronger than the star's own gravity that holds it together. The star is gently pulled apart, its gases unwound into long, flowing streams that then join the accretion disk. This tidal disruption event is a rare and beautiful cosmic phenomenon, a star's final, brilliant offering to the silent giant. The process is not an explosion, but a quiet unraveling, a peaceful deconstruction of a star into its constituent parts, which then join the slow, luminous spiral. Through this patient process of accretion, black holes grow over cosmic timescales. The supermassive black holes at the centers of galaxies, like our own Milky Way's Sagittarius A, have grown to their immense size by slowly gathering the gas, dust, and stars that have drifted into the heart of the galaxy over billions of years. It is a slow, silent, and steady process, a fundamental part of galactic evolution. It is not an act of destruction, but of cosmic recycling, where matter is not lost, but transformed and added to the quiet, gravitational heart of the galaxy. Having explored the serene and familiar darkness of a black hole's exterior, we now turn our thoughts inward toward its heart. Here, in the center, our understanding of the universe softens into a gentle whisper, a quiet and beautiful riddle that has puzzled and inspired the most thoughtful minds for a century. Let us drift past the silent threshold of the event horizon and journey together into this gentle mystery. Our journey continues inward. Having crossed the peaceful, invisible boundary of the event horizon, we are now carried by the gentle, inexorable flow of space-time itself. All paths lead to the center. Everything that has ever crossed this threshold, every particle of dust, every stream of gas, the light of every captured star is on this same final pilgrimage. It is a quiet convergence, a journey toward the very heart of the black hole. According to the beautiful and elegant equations of Albert Einstein's theory of general relativity, this journey ends at a single, infinitesimal point, the singularity. Let us be gentle with this word, for it carries with it a great weight of misunderstanding. We often imagine a singularity as a tiny, hard, and terrifying object, a point of infinite sharpness. But in the language of physics, a singularity is something far more subtle and profound. It is not a place, but a moment. It is a point in space-time where our understanding, as described by general relativity, comes to a peaceful and respectful stop. Imagine drawing lines on a globe. The lines of longitude all meet at the North Pole. At that single point, the concept of east and west loses its meaning. The singularity is like that, but for the laws of physics themselves. It is the point where the density of matter and the curvature of space-time are calculated to be infinite. The word infinity itself is not a number we can count to. It is a mathematical concept that signals a limit has been reached. It is a signpost that the theory we are using, as powerful and as accurate as it is, can no longer describe the reality in front of it. Think of a microphone recording a beautiful, quiet melody. As the music gets louder, the recording is clear. But if the sound becomes overwhelmingly loud, the microphone is saturated. The recording becomes a distorted, flat line, unable to capture the true nature of the sound. The singularity is like that flat line in our recording of the universe. It tells us that the physics of general relativity, the language we are using to listen to the cosmos, has been overwhelmed by the extreme conditions at the heart of a black hole. So, the singularity is not a monster hiding in the dark. It is a profound and gentle question mark, placed right at the center of our most extreme cosmic theories. It is the universe's way of whispering to us that the story is not yet complete. It is the place where the two grand pillars of 20th century physics must finally meet and reconcile. One of these is general relativity, the theory of the very large, of stars and galaxies, and the graceful curve of space-time. The other is quantum mechanics, the theory of the very small, of atoms and particles, and the strange, shimmering dance of energy and probability. In our everyday world, these two realms are separate. But in the heart of a black hole, an immense galactic-scale mass is crushed down to a subatomic size. Here, the very large meets the very small, and a new understanding is required. Scientists believe that a true theory of quantum gravity, a theory that can unite these two great ideas, would be able to describe what truly happens at the center of a black hole. In such a theory, the infinity would likely disappear, smoothed out into something new and wonderfully strange, something finite and physical. The singularity, then, is a beautiful placeholder. It is a symbol of our quest for deeper knowledge, a quiet beacon calling us toward a more complete understanding of reality. It is a place of infinite mystery, not infinite terror. It is the silent beating heart of a cosmic riddle, a peaceful enigma that invites not fear, but a deep and quiet sense of wonder. As we continue our quiet contemplation of this central point, this singularity, let us explore the gentle implications of what it represents. To imagine all the mass of a colossal star, or even millions of stars, compressed into a space with zero volume, is a thought that stretches the very fabric of our imagination. It is a cosmic koan, a simple statement that contains a universe of complex, interwoven ideas. It is here that the familiar world of cause and effect, of space and time, seems to dissolve into a gentle, silent hum of pure potential. In our universe, everything we know has dimensions. It has a height, a width, a depth. Even the smallest particles that make up our world occupy some space, however fleetingly. But the singularity, as described by general relativity, is different. It is a point of pure geometry, a location without size. All the rich and complex history of a star, its fiery birth, its long life of shining, its final, dramatic collapse is reduced to a set of coordinates on a cosmic map. The physical star is gone, and what remains is pure, concentrated gravity. This idea challenges our most fundamental intuitions about the nature of existence. Let us think about the laws of physics that govern our lives. They are predictable, reliable. If you let go of a stone, it will fall. The sun will rise tomorrow. These laws are written in the language of space and time. But at the singularity, where space-time itself is thought to come to an end in a point of infinite curvature, these laws can no longer be written. The stage upon which the play of the universe unfolds has itself vanished. This is the ultimate expression of the breakdown of our known physics. It is not that the universe becomes chaotic, but that our language for describing it becomes silent. This concept has been a source of profound and peaceful contemplation for physicists for decades. It is a puzzle that is not meant to be solved with force, but with a new way of seeing. Some have wondered if the singularity is a gateway, a point where our universe connects to another. Others have imagined that the intense quantum effects at this scale might cause the collapsing matter to rebound, to spring back and create a new, young universe within the black hole. These are not settled theories, but beautiful streams of thought, flowing from the single, quiet question of the singularity. Holding this idea in your mind should not be a strain. Let it be a soft, wondrous thought. Imagine all the complexity of a forest, every tree, every leaf, every ray of sunlight being contained within a single tiny seed. The singularity is a similar concept, but for the fabric of reality itself. It suggests that the universe has a way of holding immense complexity in a state of profound simplicity. It is the ultimate expression of cosmic potential, a silent point from which, perhaps, new realities could be born. It is a gentle reminder that even in the places of greatest extremity, the universe follows a logic that is beautiful, deep, and for now, just beyond the reach of our quiet understanding. From the gentle riddle of the singularity, we now drift to another, related puzzle that whispers from the edge of the black hole. This puzzle is not about the center, but about what is lost along the way. It is called the information paradox, and it is born from a quiet conflict between the two great theories we have met. On one hand, the world of quantum mechanics, which governs the small, has a fundamental rule: information can never be destroyed. On the other hand, general relativity seems to suggest that black holes are the ultimate destroyers of information. What do we mean by information? In this sense, it is not just the words in a book or the data in a computer. In physics, information is the unique, detailed description of every particle in the universe. It is the story of that particle, its location, its speed, its spin, its energy. It is the complete set of properties that makes a particle what it is and distinguishes it from every other particle. The laws of quantum mechanics state with great certainty that this information is always conserved. It can be rearranged, it can be scrambled, but it can never be truly erased from the universe. If you burn a log in a fireplace, it might seem that the information in the wood is gone forever. But in reality, it is all still there, encoded in the precise state of the smoke, the ash, the heat, and the light that is released. With perfect knowledge, you could theoretically reconstruct the log from its remnants. Now, let us turn back to our black hole. When a particle, with all of its unique information, falls across the event horizon, it travels to the singularity, and there, according to general relativity, it is crushed out of existence. Its mass is added to the black hole, but its individual story, its unique set of properties seems to be gone forever. A black hole, in this simple picture, is described by only three things: its mass, its spin, and its electric charge. It doesn't matter if it was made from a collapsed star, a cloud of dust, or a library of books. Once inside, all the intricate details are lost, and only the total mass, spin, and charge remain. This presents us with a gentle but profound conflict. If the quantum rules are correct, the information must be preserved somewhere. But if the simple picture of a black hole is correct, the information is gone. This is the information paradox. It is a quiet contradiction at the heart of our understanding of the cosmos. Where do the lost stories go? The light, the matter, the history of everything that falls into a black hole, is it truly wiped from the cosmic ledger? For decades, this question has inspired a deep and peaceful debate. It has been a central driving force in the search for a theory of quantum gravity, as such a theory must surely hold the answer. The resolution to this paradox is not just a matter of cosmic accounting. It touches upon the very nature of reality, of time, and of what it means for something to exist. The search for an answer is a search for a more complete story, a story where the tales of falling stars and drifting dust particles are not lost in a silent void, but are somehow, somewhere, woven back into the grand and eternal tapestry of the universe. Just as this gentle riddle of lost information was settling into the minds of physicists, a new and beautiful idea emerged, one that seemed, at first, to make the puzzle even deeper. In the 1970s, the physicist Stephen Hawking, while thinking about the strange intersection of quantum mechanics and the event horizon, made a remarkable and quiet discovery. He realized that black holes are not perfectly black. They should, in fact, glow with a faint warmth. This glow is now known as Hawking radiation. Imagine the vacuum of empty space. In the quantum world, this vacuum is not truly empty. It is a shimmering, vibrant place where pairs of virtual particles, a particle and its antiparticle, are constantly popping into existence and then annihilating each other in a flash of energy too. Quick to be noticed. This is the normal, gentle hum of empty space. Hawking realized that if one of these particle pairs happens to appear right at the edge of a black hole's event horizon, something different can happen. It is possible for one particle of the pair to fall across the horizon, while the other particle escapes into space. To a distant observer, it would look as though the black hole has just emitted a particle. The particle that fell in has a kind of negative energy, which, when absorbed by the black hole, ever so slightly reduces its total mass. The particle that escaped carries away positive energy. The net result is that the black hole very slowly, particle by particle, loses mass and radiates energy. It is like a piece of cosmic coal, glowing with a very low heat, and very slowly turning to ash. This process is incredibly slow. For a black hole the mass of our Sun, it would take an unimaginably long time, vastly longer than the current age of the universe, for it to evaporate completely. For the supermassive black holes in the centers of galaxies, the process is even slower. But, given enough time, in a future so distant it is almost beyond comprehension, every black hole is predicted to eventually fade away in a final, gentle puff of radiation. This beautiful idea, however, added a new layer to the information paradox. If a black hole can completely evaporate, then what happens to the information it once held? The radiation that it emits, in Hawking's original calculation, appears to be random, like the featureless hiss of static. It does not seem to contain the rich, detailed stories of all the things that fell in. So, if the black hole disappears, and the information is not in the radiation it leaves behind, then it seems the information is truly, finally, lost. This made the quiet conflict even more profound, and the search for a resolution even more important. And so, we find ourselves in a place of gentle contemplation. We have, on one side, the beautiful geometric world of general relativity, which gives us the event horizon and the singularity. On the other, we have the precise, unyielding rules of quantum mechanics, which tell us that the stories of the universe can never be lost. The discovery of Hawking radiation, this faint and fading glow, brought these two ideas into a direct yet peaceful conflict. It became clear that something in our understanding was incomplete. This is the nature of science. It is not a collection of settled facts, but a living, breathing process of inquiry. When a paradox like this arises, it is not a sign of failure. It is a gift. It is a gentle signpost, pointing the way toward a deeper, more harmonious understanding of the cosmos. The search for a resolution to these puzzles, the problem of the singularity and the information paradox, was not a frantic race, but a calm, meditative process of thought, of exploring new ideas, and of questioning our most basic assumptions. Physicists began to wonder, what if the story of a collapsing star doesn't end with a singularity at all? What if, in the final moments of its collapse, just before an event horizon can form, a new kind of physics takes over? A physics that brings the gentle rules of the quantum world to the forefront and stops the collapse in its tracks. Perhaps the universe has a softer answer, a way to create an object that is incredibly dense, incredibly massive, but that avoids these infinities and paradoxes altogether. This search for a softer answer has led to some of the most beautiful and creative ideas in modern physics. It is a quiet rebellion against the seeming absolutes of the black hole. It is a search for an alternative ending to the story, an ending that is just as wondrous, but perhaps more complete. Scientists began to imagine other possibilities, other kinds of incredibly compact objects that might exist in the deepest parts of space, hiding in plain sight, mimicking the appearance of black holes, but built on an entirely different, more stable foundation. This is the gentle current of thought that carried us to the shore of a new idea. It is a testament to the patient, persistent nature of human curiosity. We are not content with paradoxes. We seek harmony. We seek a story of the universe that is whole and consistent and beautiful from every angle. And so, with this peaceful desire for a more complete picture in our minds, we now turn away from the familiar darkness of the black hole and prepare to welcome the birth of a new idea, a new possibility in the cosmic night. Leaving behind the gentle riddles of the black hole, our journey now takes a turn. We move from the established shores of knowledge into the calm, open waters of a new and elegant theory. Here, we will witness the birth of an idea designed to bring peace to the paradoxes we have just explored. This is the story of the Gravastar. Every great idea in science begins not with a thunderous discovery, but with a quiet question. Our story begins in the early years of the 21st century, with two physicists named Paul Mazur and Emil Motola. Let us picture them not as revolutionaries trying to tear down old ideas, but as thoughtful stargazers, as quiet architects of a new cosmic possibility. They looked at the elegant structure of Einstein's theory of relativity, and they looked at the deep puzzles of the singularity and the information paradox, and they asked a simple, gentle question: what if there is another way? Their work was part of a long tradition of scientific inquiry, a peaceful and continuous conversation stretching back through the decades. They were not the first to feel a sense of unease with the idea of the singularity, or to worry about the loss of information. For years, many in the scientific community felt that these were signs that our understanding was incomplete, that nature would surely find a way to avoid these infinite, paradoxical endpoints. Mazur and Motola's contribution was to propose a specific, concrete, and beautiful alternative. They were inspired by ideas from other areas of physics, particularly the study of how matter changes from one state to another. We see these changes all around us in our daily lives. Liquid water, when it becomes cold enough, does not simply get colder and colder forever. At a specific point, it undergoes a dramatic transformation, a phase transition, and becomes ice. Its properties change completely. It becomes a solid, crystalline structure. Mazur and Motola wondered if something similar could happen to the very fabric of space-time itself. They imagined the final moments of a collapsing star. As the matter becomes ever more dense, as gravity becomes overwhelmingly strong, perhaps it reaches a critical point, a threshold, just like water at its freezing point. And at this threshold, perhaps space-time itself undergoes a phase transition. Perhaps it transforms into a new and exotic state of being, something that is not a singularity, but something else entirely. This was the seed of their idea, a quiet thought that would grow into a complete and elegant theoretical structure. Their work, published in the early 2000s, was a testament to the power of creative, peaceful thought. It was a mathematical journey, an exploration of what was possible within the known laws of physics, if one was willing to look from a slightly different angle. They were not trying to prove black holes wrong, but rather to suggest that the universe might have more than one option for its most massive, collapsed objects. They were gentle architects, drawing up a blueprint for a new kind of cosmic home. A home built not on a foundation of infinite collapse, but on a foundation of perfect, balanced, and stable quantum principles. Their work opened a new door in our cosmic imagination, inviting us to look into the darkness and see not a void, but a structure. The core idea that Mazur and Mottola introduced, the very heart of their proposal, is the concept of a gravitational phase transition. To understand this, let us return to the gentle, familiar image of water. Water is a beautiful and simple substance, but it can exist in three very different states, or phases: as a gas, which is steam, as a liquid, which is the water we drink, and as a solid, which is ice. These phases are all made of the same molecules, but the way those molecules are arranged and the way they interact with each other is completely different in each state. A phase transition is the process of changing from one state to another. When water boils, it transitions from a liquid to a gas. When it freezes, it transitions from a liquid to a solid. These transitions happen at a very specific temperature and pressure. They are not gradual changes, but sudden and complete transformations. At the moment of freezing, the freely flowing molecules of water suddenly lock into a rigid, crystalline structure. A new kind of order emerges. This is a fundamental process of nature, a way for matter to find a new, stable arrangement when its conditions change. Mazur and Mottola's profound and gentle insight was to apply this same principle not to matter, but to the fabric of space-time itself. In Einstein's theory of general relativity, gravity is not a force, but a property of space-time. Mass and energy tell space-time how to curve, and the curvature of space-time tells matter how to move. The two are deeply, inextricably linked. The substance that is collapsing at the heart of a dying star is not just matter. It is matter, energy, space, and time, all woven together. They propose that as a star collapses, the energy density, the concentration of mass and energy, reaches an unbelievably high, but finite, value. A value so extreme that it triggers a phase transition. In their model, the very fabric of space-time inside the collapsing star undergoes a quantum mechanical shift, transforming into a new and exotic state. This new state of space-time is fundamentally different from the ordinary space-time outside. It is a state that resists further compression. It pushes back against the inward pull of gravity. Imagine you are squeezing a soft rubber ball in your hand. You can squeeze it smaller and smaller, but at a certain point, you can't squeeze it anymore. The material itself pushes back against your hand. The cosmic phase transition proposed by Mazur and Mottola is like that, but on a far grander and more fundamental scale. The collapse of the star is halted, not by a familiar pressure, like in a normal star, but by the emergence of this new, exotic state of space-time. This new state is a form of what is called a Bose-Einstein condensate. This is a known state of matter that can be created in laboratories at extremely cold temperatures, where all the individual atoms in a substance lose their individual identities and begin to behave as a single, collective quantum entity. Mazur and Mottola suggested that the gravitons, the hypothetical quantum particles of gravity, could form such a condensate under the extreme conditions of a stellar collapse. The result is an object that is held up by the collective quantum pressure of space-time itself. The catastrophic, endless collapse into a singularity is completely avoided. Instead, the star settles into a new, stable, and final form. Having understood the gentle, yet profound, idea of a cosmic phase transition, we can now formally introduce the beautiful object that is born from it. Mazur and Mottola gave their creation a descriptive and elegant name, the Gravastar. This name is a shorthand for a longer, more technical term, a gravitational vacuum star. Each part of this name tells us something important about the nature of this theoretical object, painting a picture of its unique and harmonious structure. Let's begin with gravitational. This tells us that the object is, first and foremost, a creature of gravity. It is formed by the immense gravitational collapse of a massive star, and it is held together by its own powerful gravitational field. From a distance, its gravity would be indistinguishable from that of a black hole of the same mass. It would bend light in the same way, and it would hold stars and planets in orbit in the same way. It is a full participant in the cosmic dance of gravity. Next, let us consider the word vacuum. This is perhaps the most surprising and beautiful part of the idea. It tells us that the interior of this object is not filled with crushed matter, as one might expect. Instead, the phase transition creates a core that is a region of pure vacuum energy. It is a bubble of a different kind of spacetime, a spacetime that is inherently repulsive. This is the de Sitter space we will explore later, a kind of spacetime that naturally wants to expand. So, at its heart, the Gravastar is a pocket of energetic, expansive nothingness. It is this vacuum core that provides the outward pressure to resist the pull of gravity. Finally, we have the word star. This tells us that, unlike a black hole, the Gravastar is considered to be a physical object. It has a structure, it has layers, and most importantly, it has a surface. It is not a hole in the fabric of reality, but a new and stable endpoint for the life of a star. It is a star made not of hot gas, like our sun, but of the very fabric of spacetime, rearranged into a new and perfect form. So, the Gravastar is a gravitational vacuum star. It is a three-layered cosmic structure. On the outside, there is an infinitesimally thin shell of the original, collapsing matter, frozen at the moment of the phase transition. Just inside that is a layer of the exotic new state of spacetime created by the transition. And at the very center, there is a core of repulsive vacuum energy. It is a celestial bubble, a delicate and yet incredibly strong structure, born from a cosmic change of state. It is an object that offers a solution to the puzzles of the black hole, not by adding complexity, but by revealing a new and profound simplicity. Now we arrive at the most peaceful and satisfying aspect of the Gravastar theory. By its very nature, by its very architecture, the Gravastar model completely avoids the need for an infinitely dense singularity. This is not a small detail, it is the entire point. It is the gentle and elegant solution to the riddle that has sat at the heart of black hole physics for a century. Let us recall our journey into the black hole. The collapse of matter was unstoppable. Gravity, in the theory of general relativity, had no known opponent at this scale, and so the matter was destined to be crushed into a single point of infinite density. This infinity, this singularity, was a sign that the theory had reached its limit, a place where the physics we know becomes silent. The Gravastar, however, provides an alternative path. In the Gravastar model, the collapse is halted before a singularity can ever form. The phase transition of spacetime itself provides the support that was missing. The outward-pushing vacuum energy of the central core perfectly balances the inward-pulling force of gravity. The Gravastar settles into a state of perfect, eternal equilibrium. There is no endless collapse. There is no point of infinite density. There is no place where the laws of physics break down. Instead of a singularity, the Gravastar has a core of smooth, well-behaved spacetime. It is a place that our current laws of physics can, in principle, describe and understand. The curvature of spacetime is incredibly high, but it is finite. The density of energy is enormous, but it is finite. All the infinities that troubled us in the black hole model have been replaced by finite physical values. This is a profoundly comforting idea. It suggests a universe that is more harmonious, a cosmos that does not contain points where it is fundamentally unknowable. It replaces a mathematical paradox with a physical structure. The question mark at the center of the galaxy is replaced with a beautiful, stable, and understandable object. This solution feels more whole, more physically intuitive. Nature, in its wisdom, often seems to avoid true infinities, finding elegant ways to resolve them. The Gravastar is a perfect example of this kind of elegant resolution, born from the quiet and creative contemplation of the universe's deepest laws. Having removed the singularity from the center, the Gravastar theory also transforms the nature of the object's boundary. A black hole is defined by its event horizon, that silent, invisible threshold of no return. The event horizon is not a physical thing, it is a boundary in space-time. The Gravastar, however, is different. Because the collapse is halted just before an event horizon can form, the Gravastar does not have one. Instead, it has a physical, albeit incredibly exotic surface. Let us try to visualize this. Imagine you are traveling towards a black hole. You cross the event horizon without noticing, and then you are inside, with no possibility of escape. Now, imagine you are traveling towards a Gravastar of the same mass. Your journey would be very similar at first. The pull of gravity would be identical, but just as you reach the point where the event horizon would have been, you would encounter something else. You would encounter the physical shell of the Gravastar. This shell is theorized to be infinitesimally thin, a delicate membrane made of the very matter that was collapsing to form the object. This matter is held in a state of suspended animation, frozen at the very edge of the phase transition. It is a boundary that you could, in principle, touch. It is a place where the Gravastar ends and normal space begins. This is a profound difference. An event horizon is a one-way door into a region of broken physics. A Gravastar's surface is the edge of a stable physical object. This surface would be a place of unimaginable extremes. The gravity would be so strong that time would slow down to an almost complete stop relative to a distant observer. From our perspective, anything that fell onto the surface would appear to freeze, just as it would at the event horizon. The light from an object at the surface would be stretched to incredible wavelengths, becoming almost infinitely redshifted. To an outside observer, distinguishing between a Gravastar's surface and a black hole's event horizon would be incredibly, perhaps impossibly, difficult. But for the object itself, the difference is everything. An object hitting the surface of a Gravastar would be destroyed by the immense forces, its matter and information added to the substance of the shell. But it would not be lost from the observable universe. It would not be drawn into a singularity. Its story would become part of the surface, not erased in a void. This idea of a physical boundary, a tangible end to the object, brings a sense of order and place back to this exotic corner of the cosmos. It replaces the unsettling concept of a one-way portal with the more intuitive, more comforting idea of a solid, stable, and real cosmic body. As we conclude this first look at the birth of the Gravastar idea, let us pause and reflect on its deep and quiet elegance. The concept of the Gravastar is more than just a clever alternative to the black hole. It is an attempt to bring the two great pillars of physics, general relativity and quantum mechanics, into a more peaceful and unified story. It is a bridge between the world of the very large and the world of the very small. The black hole, as described by general relativity alone, stands in gentle conflict with the quantum world, primarily through the information paradox. It creates a scenario where the fundamental quantum rule of information conservation appears to be violated. This has been a source of deep, quiet tension in physics for half a century. The Gravastar, born from a quantum phase transition, resolves this tension beautifully. By preventing the formation of an event horizon and a singularity, the Gravastar ensures that information is never lost. When matter falls onto the Gravastar's surface, its information is not erased. It is simply absorbed and encoded onto that physical surface. The story is not lost, but preserved. This brings the story of stellar collapse back into harmony with the quantum laws that govern the rest of the universe. The Gravastar is a testament to the idea that the universe is, at its deepest level, consistent and whole. It suggests that the strange and wonderful rules of quantum mechanics are not just for the world of tiny particles, but can play a decisive role on the grandest of cosmic stages. It is a vision of a universe where gravity and the quantum world do not fight, but work together to create structures of profound stability and beauty. It is a more complete, more harmonious picture, a quiet symphony of physics where every instrument plays its part, and no note is ever truly lost. Our journey now takes us to the very structure of the Gravastar itself. We will begin our exploration on the outside, at its delicate and yet impossibly strong boundary. This is the outer shell of stillness, the first of the three layers that make this object a bastion of perfect cosmic equilibrium. Let us imagine ourselves floating in the deep, silent space near a Gravastar, From our safe distance, it would appear as a perfect sphere of darkness, its immense gravity bending the starlight behind it, creating a familiar-looking silhouette against the cosmos. But as we drift closer in our minds, we focus on its boundary, the place where the Gravastar meets the universe. Here we find its first layer, the outer shell. This shell is theorized to be an incredibly thin, yet unimaginably dense sphere of matter. It is the final resting place of the very star that collapsed to create this object. Think of the collapsing star in its final moments. A sphere of matter, more massive than our Sun, is falling inward upon itself at nearly the speed of light. In the Gravastar model, this collapse is suddenly and completely halted by the phase transition occurring within. This outer shell is that matter, frozen at the very instant the transition took place. It is a sphere of matter held in a state of perfect, suspended animation. It is neither falling inward nor expanding outward. It is held in a state of absolute, profound stillness. The matter in this shell is not like anything we could ever experience. It is compressed to a density that borders on the physically possible, a density comparable to that of an atomic nucleus, but stretched out over a sphere many kilometers wide. Some physicists have described this shell as being like a kind of perfect crystalline solid. Its constituent particles are locked into a rigid structure, not by chemical bonds, but by the immense, balanced forces of gravity pulling in and the pressure of the vacuum core pushing out. Imagine the surface tension on a single perfect drop of morning dew. It is a thin, invisible skin that holds the water together in a beautiful sphere, resisting the pull of gravity that tries to flatten it. The outer shell of a Gravastar is a cosmic version of this, but on an unimaginable scale. It is a delicate skin, perhaps only a few atoms thick, yet it is strong enough to withstand the most extreme gravitational forces in the universe. It is the container that holds the exotic physics of the Gravastar's interior, separate from the rest of the cosmos. This shell is also the interface between the Gravastar and the outside universe. Any matter or energy that falls onto the Gravastar does not pass through this shell. Instead, it merges with it, becoming part of its structure. Its mass is added to the total mass of the Gravastar, and its information is encoded onto the surface. It is a boundary that is both perfectly impenetrable and perfectly absorbent. It is a sphere of perfect stillness, a silent crystalline monument to the star that once was, now transformed into the serene and stable guardian of a cosmic secret. Part 4b. The nature of exotic matter. 901,100 words. Flowing from the idea of this thin crystalline shell, we must now gently explore the substance from which it is made. In the Gravastar model, this shell is composed of what physicists call exotic matter. The word exotic might conjure images of something strange or unnatural, but in physics, it has a very specific and peaceful meaning. It simply refers to a theoretical form of matter that has properties different from the matter we experience every day. The key to understanding this shell, and indeed the entire stability of the Gravastar, lies in understanding the gentle nature of this exotic substance. All the matter we know, from the air you are breathing to the stars in the sky, has a familiar property. It has positive pressure. If you inflate a balloon, the air inside pushes outward on the rubber skin. This is pressure. In the language of Einstein's general relativity, both energy and pressure are sources of gravity. Positive pressure, like the pressure from the air in a balloon or the heat in the core of a star, actually adds to the gravitational pull, making it stronger. This is why in a normal star, the immense pressure that holds it up also contributes to the very gravity that is trying to crush it. It is a constant, delicate battle. Exotic matter is different. It is theorized to have negative pressure. This is a concept that can feel a bit strange at first, but we can approach it with a gentle analogy. Imagine stretching a rubber band. The rubber band pulls inward, trying to return to its original state. This inward pull is a kind of tension. Negative pressure, in a cosmic sense, is like a tension that exists within the fabric of space itself. Instead of pushing outward, like the air in a balloon, a substance with negative pressure pulls inward on itself, creating an outward pushing gravitational effect. It is gravitationally repulsive. This is a profound and beautiful idea. It means that while exotic matter still has positive energy and is attracted to other matter by gravity, its internal state of being, its negative pressure creates a kind of anti-gravity. It is a form of cosmic buoyancy. Think of a cork held under water. The water pushes it upwards, not because the cork has a magical upward force, but because it is less dense than the water around it. In a similar way, exotic matter with negative pressure pushes outward against the curve of space-time, resisting the compression of gravity. In the context of the Gravastars shell, this property is crucial. The matter in the shell is theorized to be in a state where its pressure is equal in magnitude but opposite in sign to its energy density. This specific state, where pressure equals negative energy density, is the defining characteristic of the substance that makes up the shell. It is this perfect balance that allows the shell to exist in its state of profound stillness. The inward pull of its own immense mass energy is perfectly and locally counteracted by the outward push of its own negative pressure. This exotic matter is not something that physicists have simply invented out of thin air. The equations of general relativity allow for its existence, and similar concepts appear in other areas of cosmology. For instance, the mysterious dark energy that is causing the expansion of our universe to accelerate is believed to be a form of energy with strong negative pressure. So, the substance that holds a gravastar together may be related to the very substance that is gently pushing our entire universe apart. It is a universal principle, a fundamental property of space-time, manifesting in a different form. The gravastar, then, is a small, contained example of a cosmic principle that governs the destiny of the entire universe. It is a quiet testament to the strange and wonderful possibilities that lie sleeping within the elegant equations of physics. Part 4c. Resisting the inward pull. 750-900 words. Having learned the gentle properties of this exotic matter, we can now understand how it performs its most crucial task, resisting the immense, inward pull of gravity. In a normal star, this resistance is provided by the heat and pressure from nuclear fusion in its core. But for an object as compact as a gravastar, a far more powerful and stable force is needed. This is the role of the negative pressure within the outer shell. Let us return to our image of the balanced forces. On one side, we have the relentless pull of gravity. The gravastar contains the mass of several suns packed into a sphere only a few kilometers across. This creates a gravitational field of almost unimaginable strength, a steepness in space-time that is constantly trying to pull the object into an even smaller point, to continue the collapse towards a singularity. This is the inward force, a silent and powerful cosmic weight. On the other side, we have the gentle, yet unyielding resistance of the shell itself. The exotic matter of the shell, with its profound negative pressure, acts as a perfect counterbalance. This is not a violent explosion pushing outward, but a fundamental property of the material itself. The very fabric of this exotic shell is in a state of tension, and this tension manifests as a repulsive gravitational force. It is a perfect internal buoyancy that says no further. Imagine trying to push the north poles of two powerful magnets together. As they get closer, a powerful, invisible force pushes them apart. You can feel the resistance growing the harder you push. The negative pressure of the Gravastar's shell provides a similar kind of resistance to the compression of gravity. The more gravity tries to squeeze it, the more the shell's repulsive nature pushes back. This allows it to find a point of perfect equilibrium, a size at which the inward pull and the outward resistance are in a flawless, silent balance. This is a fundamentally different kind of stability than that of a normal star. A star like our Sun is in a constant, dynamic process. It is burning fuel, radiating energy, and will one day change and die. The stability of the Gravastar shell is static, permanent. It is not burning anything. It is a final resting state of matter and space-time. The balance is built into the very nature of its substance. It does not need fuel to maintain its resistance. It can, in theory, remain in this state of perfect balance for eternity. So, when we picture this thin, crystalline sphere, we should see it not just as a passive container, but as an active and essential component of the Gravastars' existence. It is the silent warrior on the front line of the battle against gravitational collapse. But it is a battle that has already been won. The forces are perfectly matched. The war is over. What remains is a state of eternal, peaceful stillness, a monument to the perfect balance that can be achieved when the gentle, repulsive nature of exotic matter stands in quiet opposition to the immense inward pull of gravity. Part 4. A perfect balance. 650 words. Let us now take a moment to simply be with this idea of a perfect balance. Let your mind rest on this image of the Gravastars' outer shell. Here, at the very edge of what could have been a black hole, two of the most powerful forces imaginable are held in a state of absolute, serene equilibrium. It is a cosmic stillness that is almost poetic in its perfection. On one hand, there is the force that builds galaxies and holds worlds in their orbits. Gravity. In this small region of space, gravity is at its most extreme. A relentless and overwhelming desire for all matter and energy to fall together into a single point. It is the universe's tendency toward ultimate compression, the final act of a dying star's collapse. It is a force of immense, silent power, pulling everything inward with a strength that seems, by all rights, to be irresistible. And yet, on the other hand, there is its perfect opposite. A force born not from familiar physics, but from the deep quantum nature of space-time itself. The negative pressure of the exotic shell, a form of cosmic tension, provides a precise and equal outward push. It is not an explosion. It is not a temporary reprieve. It is a fundamental property, a permanent and unwavering resistance. It is the universe's deep structural integrity, its refusal to be broken by its own weight. Picture a perfectly constructed archway of stone. Each stone pushes against its neighbors, and the force of gravity pulling down on them is perfectly redirected, creating a structure of immense strength and stability. The archway stands not because of some active, energy-consuming process, but because its geometry and materials have achieved a state of perfect balance. The outer shell of the Gravastar is like this, but for the fundamental forces of the cosmos. It is an archway built against the weight of a collapsing star. There is no struggle here. There is no tremor, no vibration, just a deep, abiding quiet. It is a stillness born from the perfect cancellation of two immense and opposing potentials. The desire to collapse is met with an equal and opposite desire to resist. The result is a state of being that is unchanging, eternal. It is a monument to equilibrium, a demonstration that even in the most extreme environments the universe can imagine, a state of perfect, peaceful balance is not only possible, but is perhaps the final, most stable answer. Chapter 5. The De Sitter Core. Having explored the serene, balanced stillness of the outer shell, our journey of the imagination now takes us deeper. We pass through this crystalline boundary and enter the very heart of the Gravastar. Here, we find something even more surprising, something that defies our expectations of what the center of a collapsed star should be. We enter the De Sitter Core. Part 5. Journeying to the center 650 words. Let us begin this next phase of our journey with a gentle transition. We leave the dense, crystalline outer shell behind. In our minds, we pass through this infinitesimally thin layer, this boundary where the laws of physics transform. And as we emerge on the other side, the experience is not one of entering a place of even greater pressure and density. Instead, it is a feeling of release. It is a feeling of entering a vast, open, and silent space. The journey to the center of a Gravastar is unlike any other. If you were to journey to the center of a planet, a star, or even a neutron star, you would encounter ever-increasing density, ever-mounting pressure. The closer you get to the core, the more crushed and compact the matter becomes. But here, the opposite is true. Once we pass through the shell, the density and pressure fall away to almost nothing. We have entered the Gravastar's core, and we find it is a near-perfect vacuum. Imagine floating in the deepest, most empty part of intergalactic space, far from any star or galaxy. There is a profound sense of quiet, of emptiness, of immense and peaceful space. The core of a gravastar is thought to be like this. It is a pocket of emptiness, a bubble of pure space-time, held within the protective embrace of the outer shell. This journey to the center is a journey into a different kind of reality. We have left the realm of matter behind and entered a realm of pure geometry. The core is not filled with the crushed remnants of the original star. All of that matter was left behind, frozen in the outer shell. What lies at the heart of the Gravastar is a region of space-time that has undergone a phase transition. It has become something new, something that is inherently empty, yet full of energy. This transition is a gentle one. It is a movement from a place of ultimate density to a place of ultimate emptiness. It is a profound and beautiful inversion of our expectations. It is the universe revealing one of its most elegant secrets, that the way to support the greatest weight is not with an even stronger material, but with a new kind of space altogether. As we float now in this silent, empty core, we are ready to understand the nature of this strange and wonderful new reality. Part 5b, a bubble of space-time, 901,100 words. Here, at the quiet center of the Gravastar, we find ourselves floating in a vast, empty space. But this is not the ordinary vacuum of our universe. This is a special kind of space-time known as de Sitter space, named after the Dutch astronomer Willem de Sitter, who first imagined its properties. To understand this gentle concept, let us look at the universe around us. Our own universe is expanding. Galaxies are moving away from each other, carried along by the stretching of space-time itself. This expansion is currently accelerating, driven by a mysterious force we call dark energy. De Sitter space is a theoretical model of a universe that contains nothing. But this dark energy, imagine a universe with no stars, no galaxies, no matter at all, just a pure, empty vacuum, filled with a uniform, positive energy. In Einstein's theory of relativity, this vacuum energy has a remarkable property. It exerts a negative pressure. It is gravitationally repulsive. A universe filled with it would not just expand. It would expand at an ever-accelerating rate. Every point in this universe would be pushed away from every other point by the inherent outward-stretching nature of space-time itself. This is de Sitter space. It is a cosmos with a built-in, gentle and constant outward breath. The core of a gravastar is theorized to be a finite contained bubble of this de Sitter space. It is a tiny pocket universe, nested within our own. The phase transition that occurred during the star's collapse is what transformed the ordinary space-time at the core into this new repulsive state. The extreme energy density at the center of the collapse, instead of creating a singularity, catalyzed this change, creating a stable bubble of space-time that pushes outward. This outward push is not like an explosion, which is violent and temporary. It is a gentle, persistent, and fundamental property of the space itself. Every point within the Gravastar's core is gently pushing away from every other point. This creates a constant, uniform outward pressure on the inner boundary of the outer shell. It is like the air inside a perfectly inflated balloon, always pressing outward, keeping the balloon taut and spherical. This concept is one of the most beautiful and profound in all of physics. It suggests that space-time is not just a passive stage on which the events of the universe unfold. Space-time is an active participant. It can change its state, transform its properties, and in doing so, it can create the very forces that define the objects within it. The de Sitter core of a gravastar is a perfect example of this. It is a bubble of pure geometry, a region where space-time itself provides the immense force needed to halt the complete collapse of a star. It replaces the infinite, paradoxical point of a singularity with a smooth, calm expanse of expansive space-time. It is a place of profound peace, an empty, silent core that is also the source of the gravastar's incredible eternal strength. Part 5c. The absence of matter, 750-900 words. As we continue to float in this silent, expansive core, let us linger on one of its most remarkable features, the profound absence of matter. The heart of a star is a place of incredible density, a furnace of nuclear fusion where matter is packed together under immense pressure and heat. The theoretical center of a black hole, The singularity is a point where all the star's matter is crushed to an infinite density. The core of the Gravastar is the gentle opposite of both of these. It is a realm of near-perfect emptiness. When the cosmic phase transition occurred, the collapsing star was effectively separated into two parts. The matter of the star, all the protons, neutrons and electrons, was left behind, frozen in place to form the dense outer shell. The spacetime at the center, however, completed the transition, becoming the de Sitter core. This process is a kind of cosmic purification. The core is swept clean of all the original substance of the star, leaving behind only the energy of the vacuum itself. This emptiness is not a passive void. It is a dynamic and energetic emptiness. The vacuum energy of the de Sitter space is what gives the core its repulsive properties. So, while it is empty of matter, it is full of energy. This is a key concept from modern physics. The vacuum is not nothing. It is a physical entity with its own properties, capable of exerting force and shaping the cosmos. The Gravastar's core is the ultimate expression of this idea. It is an engine powered by the energy of nothingness. Let us compare this again to the singularity of a black hole. A singularity is a place where our understanding of matter and energy breaks down. It is a point of infinite chaos. The de Sitter core, by contrast, is a place of perfect order. It is a smooth, uniform, and perfectly predictable region of space-time. It is perhaps the simplest possible structure that can exist at the heart of a massive object. It has no complex internal dynamics, no turbulence, no random motion. It is just a calm, steady outward push. This profound emptiness is what allows for the Gravastar's incredible stability. Because there is no matter in the core, there is nothing left to collapse. The final, seemingly inevitable step of gravitational collapse, the crushing of matter into a single point, is avoided because the matter has been elegantly separated and held at the boundary. The Gravastar has found a way to cheat gravitational destiny, not by overpowering gravity, but by creating a space at its center where there is nothing left for gravity to crush. It is a truly peaceful and elegant solution, a cosmic architecture built on the profound and powerful beauty of an empty space. Part 5. The Engine of Stability, 750-900 words. Now, let us connect this idea of the empty, expansive core back to the Gravastar as a whole. How does this bubble of de Sitter space act as the engine of the Gravastar's eternal stability? The answer lies in the perfect partnership between the core and the outer shell. They are two essential components of a single, harmonious system, each one's properties perfectly complementing the others. The de Sitter core, with its inherent repulsive nature, provides the constant, unwavering outward pressure. As we have seen, this is not like the thermal pressure in a star, which depends on temperature and can fade as the star runs out of fuel. The pressure from the de Sitter core is a fundamental property of the spacetime itself. It is a cosmological constant, a built-in feature of this pocket universe. As long as the core exists, it will push outward with the exact same force, forever. It is a perfect, reliable, and eternal source of support. This outward pressure is exerted on the inner surface of the outer shell. Now, let us recall the nature of that shell. It is an incredibly dense crystalline sphere of exotic matter, held together by the immense force of gravity. This shell acts as the perfect container for the de Sitter core. It is the boundary that keeps this pocket universe separate from our own. Its own immense gravitational pull provides the inward force, the containment field, that stops the de Sitter core from expanding forever. So, we have a beautiful and perfect loop of forces. The gravity of the shell holds the de Sitter core in check, preventing it from expanding. In return, the outward pressure of the de Sitter core holds the shell up, preventing it from collapsing under its own gravity. It is a state of perfect mechanical and gravitational equilibrium. The shell needs the core to avoid collapsing into a singularity, and the core needs the shell to keep it from expanding into our universe. This symbiotic relationship is the true engine of the Gravastar's stability. It is a self-sustaining system, requiring no external energy to maintain its balance. It is a final, static, and perfect arrangement of spacetime and energy. Unlike a black hole, which is the result of a runaway, unopposed collapse. The Gravastar is the result of a halted, perfectly balanced collapse. It is the universe finding a point of stability, a peaceful resolution to the immense gravitational forces unleashed by the death of a massive star. The empty core is not just a passive feature. It is the active, beating heart of this stability. The silent, invisible engine that will keep the Gravastar in its perfect form for all of time. Part 5e. A universe within 750-900 words. As we conclude our exploration of this De Sitter core, let us allow our minds to drift into a gentle, more wondrous and speculative thought. The core of the Gravastar is a bubble of De Sitter space, a self-contained, expanding pocket universe. This has led some physicists to quietly wonder, could the conditions inside a Gravastar be the seed for a new universe? This is a beautiful and profound idea, one that takes us to the very edge of our cosmic imagination. The theory of cosmic inflation suggests that our own universe began with a period of incredibly rapid, exponential expansion, driven by a field of energy very similar to the De Sitter vacuum. In a fraction of a second, the universe grew from a size smaller than an atom to a size larger than a galaxy. This inflationary period smoothed out the universe and laid the groundwork for the structures, like galaxies and stars, that we see today. It is possible that this inflation was triggered when a small patch of spacetime entered a De Sitter-like state. Now, let us look back at the Gravastar's core. We have a stable, contained region of this very same kind of spacetime. It is a pocket of inflation, held in check by the outer shell. The speculation, then, is that under certain conditions, this core might not be entirely stable. Perhaps through some quantum process, a tiny fluctuation could cause a new inflationary expansion to begin from within the core. This would not be an explosion into our universe, but the creation of a new, separate spacetime, branching off from our own. In this beautiful speculative picture, a Gravastar becomes a kind of cosmic parent, holding within it the potential for a new baby universe. The collapse of a giant star in one universe could lead to the Big Bang of another. This idea, known as cosmological natural selection, suggests that universes might reproduce and that the physical laws of a universe might evolve over generations to favor the creation of more black holes or Gravastars, as these are the mechanisms for reproduction. We must be gentle with this idea. It is not a proven theory. It is a strand of beautiful mathematical poetry, a story we tell to explore the deepest possibilities of our physical laws. It connects the end of a star's life with the birth of a new cosmos, creating a grand, cyclical, and peaceful narrative for existence. To think that within the dark, silent objects that dot our universe, there could lie the seeds of countless other universes, each with its own stars, galaxies, and perhaps even its own life, is a thought of profound wonder. It reframes the Gravastar not just as an object in our universe, but as a potential gateway to realities beyond our own, a silent, humble seed of cosmic infinity. Chapter 6. The infinitesimally thin layer. Our journey through the Gravastar's architecture has taken us through the dense outer shell and the empty inner core. Now, we focus our attention on the boundary between them. This is the third and final piece of the structure, an infinitesimally thin layer, a delicate and powerful membrane that separates these two vastly different worlds. Part 6a, the boundary between worlds, 750-900 words. Let us position our awareness precisely at the interface between the Gravastar's De Sitter core and its dense crystalline outer shell. Here lies a boundary of profound significance. It is not just a dividing line, but a distinct physical layer of its own, a membrane that is theorized to be infinitesimally thin, perhaps only the width of a single proton. Yet, within this incredibly small space, the entire transition from one form of spacetime to another takes place. It is the very location of the cosmic phase transition, frozen in time. On one side of this boundary is the outer world, the realm of ordinary matter and spacetime, albeit compressed to an incredible degree. This is the dense shell, the remnant of the original star. It is a world governed by the familiar laws of physics that build our universe. On the other side of this boundary is the inner world, the De Sitter core, This is a realm of repulsive vacuum energy, a bubble of a different kind of space-time, a place where the laws of physics manifest in a fundamentally different way. This thin layer is the wall that separates these two realities. It is the place where the phase transition is perpetually happening, yet perpetually held in a state of equilibrium. Think of the surface of a frozen lake in winter. It is a thin boundary layer where the liquid water below meets the cold air above, and at that precise interface, the water turns to ice. The boundary of the Gravastars core is like this, but it is a transition of space-time itself, not of water molecules. It is the place where normal, attractive space-time transforms into the repulsive, expansive space-time of the core. The existence of this boundary is essential for the Gravastars' stability. It is what allows two such fundamentally different regions to coexist in a stable state. It is a perfect insulator, preventing the properties of the core from leaking into our universe, and preventing the matter of the shell from falling into the core. It is a flawless and absolute separation. Visualizing this layer requires a gentle stretch of the imagination. We are talking about a fundamental shift in the nature of reality, occurring over a distance smaller than an atom. It is a place of immense energy gradients, of forces changing with incredible rapidity. Yet, in the final stable Gravastar, this region is perfectly calm and unchanging. It is a scar left over from the violent moment of the star's collapse, a scar that has healed into a line of perfect, peaceful balance. It is the silent, invisible seam that stitches two different universes together into a single, harmonious object. Part 6b, a realm of pure energy, 750-900 words. Let us now contemplate the substance of this incredibly thin boundary layer. What is it made of? In the Gravastar model, this layer is not made of matter in the traditional sense. It is not composed of protons or neutrons. Instead, it is thought to be a realm of pure, concentrated energy. It is the energetic residue of the phase transition itself, a shimmering membrane of pure physical potential. When the collapsing star's matter reached the critical density, the phase transition was triggered. This process would have released an enormous amount of energy, and it is this energy that becomes trapped and frozen in the boundary layer. It is a place where the distinction between matter and energy becomes beautifully blurred. The particles of the original star have been, in a sense, converted into a field of pure energy that lines the inner surface of the shell. Imagine the energy released in a lightning strike. For a fraction of a second, the air is transformed into a channel of blazing plasma, of pure energy. Now, imagine capturing that energy, that flash of lightning, and holding it in a permanent, stable, and infinitesimally thin spherical sheet. This gives us a faint, poetic sense of the nature of this boundary layer. It is a sphere of frozen lightning, a permanent afterglow of the moment of cosmic transformation. The properties of this energy field are unique and essential to the Gravastar's structure. It is this layer that mediates the interaction between the core and the shell. It feels the outward pressure of the de Sitter vacuum on its inner surface, and it feels the immense weight of the crystalline shell on its outer surface. It acts as the perfect transmission layer, ensuring that these two forces are communicated to each other perfectly, allowing them to find their state of perfect balance. This idea of a layer of pure energy also helps to solve one of the subtle problems of the Gravastar model. The outer shell is made of a certain kind of exotic matter, and the inner core is made of a different kind of space-time. The laws of physics often require a smooth transition between different states. This thin energy layer provides that transition. It is the in-between state, the smooth and continuous bridge that allows the universe to connect the world of the shell to the world of the core without any abrupt, violent breaks in the laws of nature. It is a place of pure energetic harmony, the silent, glowing filament that holds the entire cosmic jewel together. Part 6. The source of outward pressure. 901,100 words. Now we arrive at a deeper, more subtle understanding of the Gravastar's stability. While we have said that the de Sitter core provides the outward push, a more precise look at the model reveals that this infinitesimally thin layer plays a critical and active role in generating the pressure that holds the star up. It is not just a passive boundary, but an active participant in the cosmic balance. The true source of the outward pressure is the unique interplay of forces right at this energetic membrane. Let's revisit the properties of the two worlds this layer separates. Inside, we have the de Sitter core. This space-time is repulsive, meaning it wants to expand. This creates a natural outward push on the boundary layer. Outside, we have the dense shell of exotic matter, which is gravitationally attractive, pulling the boundary layer inward. But the story doesn't end there. The thin layer itself, being a concentration of pure energy, has its own properties, and these properties are key. According to the equations of general relativity, the pressure within a substance contributes to how it interacts with gravity. This thin layer is under immense surface tension, a force that acts along the surface of the sphere. Think of the surface of a drum, stretched incredibly tight. This tension within the boundary layer contributes to the overall pressure balance of the gravastar. In the specific gravastar model, the state of the energy in this layer is such that it creates a powerful outward force, perfectly complementing the push from the de Sitter core. So, we have two sources of outward pressure working together in perfect harmony. The de Sitter core provides a gentle, constant push from within, like a cushion of air. The energetic boundary layer then adds its own powerful repulsive force, like a tightly wound spring. It is the combination of these two effects that is strong enough to resist the almost infinite gravitational pull of the outer shell. This makes the thin layer the true heart of the gravastar's structural integrity. It is the place where the final battle against gravity is fought and won. It is a dynamic and powerful interface. It is not just a seam, but the very engine of support. The stability of the entire object depends on the precise physical state of this shimmering energetic membrane. This refined understanding gives us a more complete and beautiful picture. The gravastar is not simply a bubble of repulsive vacuum held within a shell of matter. It is a more integrated and sophisticated structure. It is a three-part system where the core, the boundary, and the shell all play an essential interconnected role. The immense stability of the gravastar arises from the perfect symphony of these three components, with the infinitesimally thin layer acting as the lead instrument, translating the repulsive nature of the vacuum core into the precise outward force needed to achieve a state of eternal, peaceful equilibrium. Part 6. A flawless separation. 750 words. Let us now reflect on the perfection of the separation provided by this thin, energetic layer. In our universe, boundaries are often messy, porous things. But here, at the heart of the gravastar, the separation between the inner and outer worlds is theorized to be flawless and absolute. This perfection is not just an aesthetic detail, it is a physical necessity for the object's long-term stability. On one side, we have the pocket universe of the de Sitter core. Its repulsive space-time must be perfectly contained. If there were any leaks, any imperfections in this boundary layer, the energy of the core could seep out, and the structure would lose its stability over time. The boundary layer acts as a perfect vessel, holding this exotic space-time in a state of permanent isolation, ensuring that its outward push remains constant and directed only at the inner surface of the shell. On the other side, we have the dense shell of matter. This matter must be prevented from ever reaching the core. If any part of the shell were to breach the boundary layer, it would fall into the repulsive de Sitter space. This would disrupt the smooth, uniform nature of the core and destroy the delicate balance of forces. The boundary layer acts as an impenetrable wall, a perfect floor holding up the weight of the shell for all eternity. This flawless separation ensures that the two realms can coexist without interfering with each other. The shell can go on being a dense, gravitationally attractive sphere of matter, and the core can go on being an empty, gravitationally repulsive bubble of space-time. Each is allowed to be its own, unique self, because this perfect, energetic membrane stands between them. It is a beautiful example of cosmic order. Out of the chaotic violence of a stellar collapse, a structure of perfect, delineated parts emerges. It is a system that has found a way to compartmentalize the most extreme forces of nature placing each one in its proper place and separating them with a boundary of mathematical perfection. This flawless separation is the secret to the Gravastars' quiet, unchanging and eternal peace. Part 6. A Symphony of Physics. 750-900 words. As we conclude our close examination of the Gravastars' internal architecture, let us zoom out and view the object as a whole, as a single, unified entity. We have explored its three distinct parts: the dense outer shell, the empty de Sitter core, and the infinitesimally thin, energetic layer that separates them. Seen together, they are not just a collection of strange components, but a beautiful and harmonious symphony of physical laws. The outer shell, the remnant of the star, plays the deep, resonant note of gravity. It is the baseline of the symphony, the immense, constant inward pull that gives the object its mass and its presence in the universe. It is the theme of attraction, of matter's desire to be together, a theme as old as the cosmos itself. The de Sitter core, the bubble of vacuum energy, plays the high ethereal melody of cosmic repulsion. It is the theme of expansion, of space's inherent desire to grow. It is a quiet, steady and unchanging note, a whisper of the force that is pushing our own universe apart. Here, captured and contained in a single, perfect sphere, it is the counterpoint to gravity's deep hum. And the thin boundary layer, the realm of pure energy, is the conductor of this symphony. It stands between the two opposing themes, ensuring they play in perfect harmony rather than clashing in a cacophony of destruction. It translates the push of the core into the precise support needed by the shell. It feels the weight of the shell and contains the energy of the core. It is the place where these two great cosmic forces meet, not in conflict, but in a perfectly balanced and resolved chord. This symphony creates a single, stable, and beautiful object. A Gravastar is a testament to the richness and creativity of the laws of physics. It shows how the universe, faced with the seemingly insurmountable problem of infinite collapse, can orchestrate a solution of profound elegance. It uses the laws of gravity, the laws of quantum mechanics, and the nature of spacetime itself, weaving them together to create a final state of being that is more stable, more harmonious, and perhaps more beautiful than the one we had imagined before. It is a silent, cosmic music, a symphony of physics playing out in the deepest, darkest corners of space. Chapter 7. A World Without a Horizon. Having come to understand the Gravastar's beautiful internal symphony, we now return to its surface to explore one of its most profound differences, from a black hole. We will contemplate what it means to be an object with a physical boundary instead of an unknowable event horizon. This is a world without a one-way door, a place with a different connection to our universe. Part 7. The Hard Surface. 750-900 words. Let us once again imagine ourselves journeying towards this massive, dark object. If it were a black hole, our journey would take us across the event horizon, that invisible and intangible point of no return. But because the Gravastar's collapse was halted, it presents us with something entirely different, a hard surface. This is not a metaphor. The theory suggests a physical boundary that an object could, in principle, make contact with. This surface is located just fractions of a millimeter above the point where the event horizon would have formed. For an object of the same mass, a black hole and a Gravastar would be almost exactly the same size. The difference is what happens at that critical radius. For the black hole, space continues on, flowing inward like a river over a waterfall. For the Gravastar, space stops. It meets the solid, crystalline shell of exotic matter. To call this surface hard is an understatement of cosmic proportions. It is a substance compressed to near nuclear density, held in a rigid state by the most extreme forces in the universe. Any object from our ordinary world that made contact with this surface would be instantly and completely obliterated. Its constituent atoms would be torn apart, and their matter and energy would be assimilated into the fabric of the shell. It is the most absolute and final of walls. The existence of this surface has profound implications. It means that the Gravastar is a part of our universe in a way that the interior of a black hole is not. The interior of a black hole is causally disconnected from us. No information can ever get out. The surface of a gravastar, however, remains part of our shared space-time. It can, in theory, interact with its environment. It can have properties like temperature and texture, even if those properties are so extreme as to be almost unimaginable. This hard surface provides a definitive end to the object. It is a clear and understandable boundary. It replaces the unsettling, abstract concept of an event horizon with something more tangible and intuitive. A black hole is a hole in space-time. A gravastar is a body in space-time. This simple distinction changes everything about how we can think and talk about these objects. It brings them out of the realm of pure mathematical abstraction and into the realm of physical, albeit exotic objects. It is a world with a shore, a final solid ground at the edge of the deepest gravitational well in the cosmos. Part 7b. Light at the Edge, 750-900 words. Flowing from this idea of a hard physical surface, let us now consider how light would behave in its immediate vicinity. Near a black hole, there is a special orbit called the photon sphere. This is a region outside the event horizon, where gravity is so strong that photons, particles of light, can be forced to travel in circles. Light at the photon sphere is like a moth circling a flame, forever trapped in an unstable orbit. If it is perturbed even slightly, it will either fly off into space or spiral down across the event horizon, lost forever. Near a gravastar, the situation is similar, but with a crucial difference. A gravastar would also have a photon sphere, a place where light can orbit. But because the gravastar has a physical surface just inside this region, the fate of light is different. A photon could, in theory, graze the very surface of the gravastar and still escape back into space. It would be an incredibly delicate cosmic dance. Imagine a beam of light sent from a distant star that passes very close to the gravastar. Its path would be severely bent by the immense gravity. As it nears the surface, it would be subject to an extreme gravitational redshift. This means the light's wavelength would be stretched, its energy lowered. From our distant perspective, the light would appear redder and dimmer. Time for this photon, from our point of view, would slow to an almost complete standstill. The gravastar's surface itself, while incredibly cold, might not be perfectly black. Quantum effects, or the slow accretion of interstellar matter, could cause it to radiate a tiny amount of energy. This light, originating from the surface itself, would have to climb out of one of the deepest gravitational wells in the universe. As it traveled away from the gravastar, it would lose almost all of its energy. The light that began as a high-energy particle on the surface might arrive at our telescopes as a very long, low-energy radio wave. So, unlike a black hole, which is defined by the perfect absorption of all light that crosses its horizon, a gravastar could have a faint, frozen halo of light at its edge. It would be a sphere of light hovering in a state of near-zero energy, a ghostly afterglow at the very brink of the void. Seeing this faint, incredibly red-shifted light would be one of the only ways to distinguish a gravastar from a black hole. It would be a whisper from the edge, a story told by light that has touched the surface of a world without a horizon, and against all odds. Return to tell the tale. Part 7c. Echoes from the Brink, 650-750 words. Another fascinating possibility that arises from the gravastar's hard surface is the idea of gravitational wave, echoes. In recent years, observatories like LIGO and Virgo have allowed us to listen to the universe, to hear the silent songs of cosmic events through the ripples they create in space-time, known as gravitational waves. When two black holes merge, they create a very specific and predictable signal. There is a chirp as they spiral closer, a final, powerful burst of energy at the moment of merger, and then a ringdown as the new, larger black hole settles into a stable state. After this ringdown, there is perfect silence. The new event horizon absorbs any trailing waves. Now, imagine if the two merging objects were not black holes, but gravastars. The initial chirp and the merger would look very similar. Two incredibly massive objects would spiral together and coalesce. But what happens after the merger would be different. Because gravastars have a hard surface and not an event horizon, the story would not end with a silent ringdown. The powerful gravitational waves created during the merger would not be entirely absorbed. Some of them could be reflected off the surfaces of the newly formed object. The gravastar, disturbed by the collision, might ring like a cosmic bell. The idea is that the boundary of the gravastar, this region between its surface and its photon sphere, could act as a resonant cavity. The gravitational waves could become temporarily trapped, bouncing back and forth between the surface and the gravitational barrier of the photon sphere. Each time these waves bounce off the surface and escape, they would create a small, subsequent pulse of gravitational waves. To our detectors on Earth, this would sound like a series of faint echoes, arriving at regular intervals after the main merger signal. It would be as if the cosmos had struck a bell, and we were hearing its faint, fading reverberations. Finding such an echo would be an extraordinary discovery. It would be a clear and unambiguous signal that the object we were observing was not a black hole. It would be the first direct evidence for a compact object with a hard surface at the event horizon scale. So far, all the signals we have detected have been perfectly consistent with merging black holes. But astronomers continue to listen, sifting through the data with great patience, hoping one day to hear a faint and distant echo from the brink. Part 7. A definable boundary. 750-900 words. Let us take a moment to reflect on the quiet comfort of a definable boundary. The event horizon of a black hole is a concept that can be deeply unsettling to our intuition. It is an intangible mathematical line that, once crossed, seals one's fate. It is a one-way portal to a region from which no return is possible, a place where our physics seems to end in a question. It is a boundary that is defined by what is lost beyond it. The hard surface of a gravastar, in contrast, offers a sense of cosmic order and place that is far more familiar to us. All the objects in our experience, from a grain of sand to a planet, have a surface. A surface is a place where an object ends and the space around it begins. It is a definable physical boundary. We can understand a surface. We can imagine touching it. We can describe its properties. By replacing the event horizon with a physical surface, the Gravastar model brings these extreme cosmic objects back into the fold of more conventional physics. It makes them part of the family of stars and planets, just an incredibly extreme and exotic member. It removes the element of the unknowable that lies at the heart of the black hole concept. With a gravastar, there is no region that is fundamentally disconnected from our universe. The object, in its entirety, exists within our shared reality. This provides a deep philosophical and psychological comfort. It suggests a universe that is, at least in principle, fully knowable. There are no magical doorways to infinity, no points where the rules of cause and effect are erased. Instead, there are just objects, made of substances with different properties, interacting according to a single unified set of physical laws. This definable boundary also offers a peaceful resolution to the information paradox. As we discussed, the paradox arises because information that falls into a black hole seems to be lost forever. But with a gravastar, there is no place for the information to get lost. When an object strikes the surface, its information is not erased. It is absorbed and imprinted onto the surface, becoming part of the physical object. The story is preserved, not lost to a void. The universe's ledger remains balanced. This sense of order, of conservation, of a cosmos with clear and definable boundaries, is one of the most gentle and appealing aspects of the Gravastar idea. Part 7. Touching the void. 901,100 words. In this final, deep contemplation of a world without a horizon, let us allow our imagination to drift to the very edge of the Gravastar's surface. Let us try to feel what it would mean for a physical object to exist in this place, to have a tangible presence at the very precipice of such immense gravity. This is, in a sense, the closest one can get to touching the void without being consumed by it. The surface of the Gravastar exists in a region of spacetime that is stretched to its absolute limit. The gravitational pull is so immense that time itself, for an observer on the surface, would be dilated almost to infinity. A single second experienced on the surface would correspond to billions of years of cosmic time for a distant observer. To be on this surface would be to exist in a state of near-perfect timelessness. From this vantage point, you could watch the entire future of the universe unfold in a fleeting moment. The forces at play here are beyond our everyday comprehension. The matter of the shell is held in a state of perfect tension, with the inward pull of gravity and the outward push of the interior forces balanced to an impossible degree of precision. It is a place where the distinction between matter and spacetime becomes beautifully blurred. The shell is not just matter. In spacetime, its properties are defined by the extreme curvature of spacetime. It is a substance woven from the very geometry of the universe. To touch this surface would be to touch a place where the fundamental constants of nature are tested to their breaking point. It is a place where the smooth, gentle curves of Einstein's relativity meet the strange, quantized world of particle physics. The Gravastar surface is the physical manifestation of this meeting point. It is the place where a theory of quantum gravity would be most vividly on display. The existence of such a surface, this tangible boundary at the edge of the void, represents a profound statement about the nature of our universe. It suggests that the cosmos does not permit true holes in its fabric. It suggests that even in the face of the most extreme gravitational collapse, reality finds a way to hold itself together, to create a final, stable, and physical object. It replaces the idea of an endless fall into nothingness with the idea of a final, solid resting place. It is a universe with a floor, a universe where even at the deepest point of a gravitational well, there is something solid beneath your feet. It is a deeply reassuring thought, a vision of a cosmos that is whole, connected, and ultimately knowable, right down to its most extreme and silent shores. Chapter 8. The Silent Guardians. We have explored the Gravastar's structure and its unique boundary. Now, let us reframe our understanding of these objects. The title of our journey tonight spoke of galactic killers more deadly than black holes. Let us now gently reinterpret this dramatic phrase and come to see Gravastars not as destroyers, but as silent, eternal guardians of cosmic order. Part 8. An eternal stability, 750-900 words. The first quality of these silent guardians is their profound and eternal stability. As we have learned, a black hole is not necessarily a permanent fixture in the universe. Through the quiet, slow process of Hawking radiation, a black hole is predicted to eventually evaporate, returning its energy to the cosmos over an unimaginably long timescale. This evaporation, however slow, means that a black hole is a temporary object, a long-lived but ultimately transient feature of the cosmic landscape. A gravastar, in contrast, is theorized to be perfectly and eternally stable. It does not evaporate. The mechanism of Hawking radiation, which arises from quantum effects at the event horizon, does not apply to a gravastar because it has no event horizon. Its hard physical surface does not produce particles in the same way. The gravastar is a closed system, a perfect equilibrium of forces that, once established, should remain unchanged for all of time. This eternal stability makes the gravastar a true final state. It is the ultimate endpoint for a massive collapsing star, a final resting form from which there is no further change. It is a cosmic monument, a structure that will endure long after all the stars have burned out, long after all the black holes have faded away into a faint mist of radiation. In the far, far distant future, in the cold, dark era of the universe, gravastars, if they exist, might be among the last massive objects remaining. Think of the difference between a cloud and a mountain. A cloud is a beautiful but temporary structure, constantly changing its shape and eventually dissipating back into the air. A mountain, on the other hand, is a symbol of permanence, a structure that endures for geological ages, a seemingly eternal feature of the landscape. A black hole is like the cloud, a long-lived but ultimately ephemeral condensation of energy. A gravastar is like the mountain, a final, static, and permanent piece of cosmic geology. This eternal stability is the source of its guardianship. It is an unchanging anchor in the ever-evolving universe. It is a silent keeper of the mass and energy it contains, holding it in a state of perfect preservation. It does not slowly leak its secrets back into the void. It simply is, a quiet and constant presence, a testament to a perfect and everlasting balance. Part 8b. The ultimate state of matter, 750-900 words. Flowing from this idea of eternal stability, we can begin to see the Gravastar as representing the ultimate state of matter and energy. In the great cosmic story of existence, matter and energy are constantly transforming. They are gathered into stars, forged into heavier elements, and scattered back into space, only to be gathered again. But what is the final, most stable configuration that a large collection of matter can possibly achieve? The Gravastar model proposes a beautiful and elegant answer. A normal star, like our Sun, is a temporary compromise. It is a battle between gravity and nuclear fusion, a state that can only be maintained as long as there is fuel to burn. A white dwarf or a neutron star are more stable states, where quantum pressure holds gravity at bay. But even these can collapse if they gather more mass. A black hole is the result of a collapse that, according to general relativity, never truly stops. It is a process of endless falling. The Gravastar, however, represents a true and final resolution. It is a state of perfect equilibrium, where the collapse has been definitively and permanently halted. It represents matter and space-time having found their most stable, lowest energy configuration. It is a state from which no more energy can be extracted. It is, in a thermodynamic sense, a perfect and final state of rest. Imagine a ball rolling down a long, bumpy hill. It might get stuck in a small valley for a while, a temporarily stable position. But a little nudge could send it rolling further down. The ultimate state is for the ball to be at the very bottom of the hill, in the lowest valley, from which it cannot roll any further. In this analogy, a normal star is high up on the hill. A neutron star is in a small valley partway down. The Gravastar is the ball at the absolute bottom of the hill. It has reached the true ground state. To be the ultimate state of matter is to be a perfect storehouse. The matter and energy that make up the Gravastar are locked into a configuration of perfect stability. They are not undergoing any further processes. They are not radiating or changing. They are simply preserved in this final, perfect form. The Gravastar is a cosmic vault, a place where the substance of a star has reached its final, most peaceful, and most enduring state of being. Part 8c. More deadly than a black hole. 901,100 words. Now we arrive at the heart of our reinterpretation. The title of our journey suggested that Gravastars could be more deadly than black holes. Let us gently unpack this word. In this cosmic context, deadly does not refer to aggression, or malice, or a desire to destroy. It refers to the sheer, absolute finality of an interaction. The deadliness of a Gravastar lies in its perfect and eternal permanence. Let's compare the fate of something that falls into a black hole with something that falls onto a Gravastar. When a particle carrying information crosses the event horizon of a black hole, its story, from our perspective, is lost. But the black hole itself is not eternal. Over countless eons, it will slowly evaporate through Hawking radiation. Many modern theories suggest that this radiation is not truly random, but is in fact a highly scrambled version of all the information that ever fell in. In this view, the information is not destroyed, but is eventually returned to the universe in a different form. The farewell is long, but it may not be final. The story is scrambled, but perhaps not erased. Now consider the Gravastar. It has no event horizon, and it does not evaporate. It is an eternal object. When a particle strikes the hard surface of a Gravastar, it is utterly and completely assimilated. Its matter and energy are added to the substance of the shell. Its unique information, its story, is imprinted onto the surface. But that surface is permanent. The information is not scrambled and returned to the universe. It is simply added to the cosmic monument and locked away there for all of eternity. This is the source of the Gravastars' greater deadliness. It is a more absolute and final resting place. An interaction with a black hole might be like having your story locked in a book that is then thrown into a fire. Eventually, the smoke and ash of the book return to the world. An interaction with a Gravastar is like having your story carved into a diamond mountain that will never, ever erode. The story is preserved, but it is also permanently removed from the dynamic, evolving narrative of the universe. It becomes a static part of a silent monument. The deadliness, then, is the deadliness of perfect preservation. It is the finality of becoming a permanent part of an unchanging object. While a black hole might eventually release its captive stories, the Gravastar acts as a silent guardian that keeps them, perfectly and forever. It is a more profound kind of removal from the cosmos, a more absolute end to an object's independent journey. It is not an act of violence, but an act of perfect and eternal assimilation. It is the quiet, final stillness of becoming one with an object that will never change. Part 8 Nick, The Keepers of Information, 650-750 words. This reinterpretation of deadliness as finality leads us to a new and beautiful role for these silent guardians. They are the ultimate keepers of information. In the quiet conflict of the information paradox, the Gravastar provides a simple and peaceful resolution. The paradox asks where the story goes. The Gravastar answers, the story is kept here, safely and forever. The surface of the Gravastar becomes a kind of cosmic library, a repository of all the history it has ever encountered. Every particle of dust, every stray photon, every stream of gas from a disrupted star that has ever fallen onto its surface has its information encoded there. The Gravastar's shell is a tapestry woven from the stories of everything it has ever touched. Unlike a black hole, where the information is thought to be hidden behind an event horizon and possibly scrambled, the information on a Gravastar's surface is, in principle, part of our physical universe. It is not locked away in a causally disconnected region. It is right there, on the surface, a tangible record written in the language of fundamental physics. Of course, we could never hope to read this library. The surface is a place of such extreme physics that we could never approach it, let alone decode the unimaginably complex quantum state of its shell. But the important thing, from a philosophical and physical perspective, is that the information is not destroyed. The fundamental laws of quantum mechanics are upheld. The universe's ledger remains perfectly balanced. In this view, Gravastars are not voids that erase history. They are archives that preserve it with perfect fidelity. They are the silent guardians of the past, holding the stories of fallen stars and ancient dust clouds in their eternal, unchanging embrace. They ensure that nothing in the universe is ever truly lost, but is instead given a final, permanent home in the grand cosmic museum. Part 8. Cosmic Monuments, 750-900 words. So let us now fully embrace our new understanding. Gravastars are not galactic killers. They are cosmic monuments. Like the Great Pyramids or ancient stone circles on Earth, they are structures of immense permanence, built to withstand the passage of ages. But instead of being built by human hands, they are built by the fundamental laws of the universe itself, sculpted by the forces of gravity and quantum mechanics. A monument is a structure that preserves a memory. The Gravastar preserves the memory of the massive star that died to create it. Its total mass is a testament to the scale of its progenitor. It also preserves the memory of everything it has assimilated since its formation. Its surface is an ever-growing chronicle of its quiet corner of the galaxy. These monuments are utterly silent. They do not shine with the fire of a star, nor do they scream with the brilliant light of an accretion disk unless they are actively feeding. For most of their existence, they would be invisible, dark spheres, revealing their presence only through their immense gravity. They are humble and unassuming guardians, performing their duty of preservation without any need for recognition. To look up at the night sky and imagine that some of the dark spaces between the stars might be filled not with holes, but with these silent, eternal monuments, is a profound and peaceful thought. It changes our perception of the cosmos. It fills the voids with substance, replaces paradoxes with structure, and transforms the concept of an end into an act of eternal preservation. These silent guardians stand as a testament to the stability and order of the universe. They represent the triumph of balance over collapse, of preservation over destruction. They are not killers to be feared, but beautiful final structures to be contemplated with a sense of quiet wonder and deep cosmic peace. They are the universe's final, most enduring sculptures, the silent monuments to the eternal laws of physics. Chapter 9. The universe's quiet hum. Having explored the beautiful theory of gravastars, from their internal structure to their philosophical implications, a gentle, practical question now arises. How could we ever know if they are real? Our journey now shifts from pure theory to the quiet, patient art of cosmic listening, as we search for faint whispers of their existence in the gentle hum of the universe. Part 9. Listening for echoes, 750-900 words. In the past, our only way to look at the universe was through light. For centuries, we have built ever larger telescopes to capture the faint photons from distant stars and galaxies, painting a picture of the cosmos in all its visual glory. But in the 21st century, humanity has developed a new sense. We have learned how to listen. We can now hear the faint vibrations of space-time itself, the gravitational waves that ripple across the universe from the most powerful and energetic events. This new sense is made possible by incredible instruments like LIGO in the United States and Virgo in Europe. These are not telescopes in the traditional sense. They are vast, L-shaped observatories with arms several kilometers long. At their heart is a system of lasers and mirrors of almost unimaginable precision. Their purpose is to measure a distance so small that it is a fraction of the width of a proton. When a gravitational wave passes by the Earth, it gently stretches and squeezes the fabric of space-time, momentarily changing the length of the observatory's arms. The detectors are sensitive enough to pick up this tiny, fleeting change. This is the quiet, patient work of modern astronomers. They are not looking through an eyepiece. They are listening to the data, to the faint hum of the universe, searching for the telltale signature of a cosmic event. It is an act of profound stillness and concentration. The detectors are so sensitive that they are shielded from the slightest terrestrial vibrations, from earthquakes to ocean waves, to the rumbling of a distant truck. All this effort is to create a space quiet enough to hear the whisper of the cosmos. This act of listening has opened a new window onto the universe. It allows us to perceive events that are completely dark, events that produce no light at all, such as the merger of two black holes. For the first time, we can directly observe the dynamics of pure gravity, the dance of space-time itself. And it is in this new, quiet symphony of gravitational waves that we might one day find the evidence we seek, the faint and distant echoes that could signal the presence of a gravastar. Part 9b. The Song of Merging Black Holes, 750-900 words. Since they began listening in 2015, these gravitational wave observatories have been incredibly successful. They have heard the songs of dozens of cosmic collisions. The most common and clearest sound they have detected is the song of two black holes merging. This sound is a beautiful and unique signature, a perfect confirmation of the predictions made by Albert Einstein's theory of general relativity a century earlier. Let us listen to this song in our minds. It begins as a low, quiet hum. This is the sound of two black holes, locked in a gravitational embrace, circling each other millions of times a second in their final moments. As they get closer and closer, they orbit faster and faster, and the hum rises in pitch and volume. This rising sound is called the inspiral. It is a cosmic crescendo, a smooth and graceful increase in frequency as the two objects race towards their inevitable union. This inspiral continues, getting higher and louder, until the two event horizons finally touch and merge into a single, larger object. At this moment, there is a powerful burst of energy, the peak of the gravitational wave signal. This is the loudest part of the song, a final, triumphant note that, for a fraction of a second, can radiate more energy than all the shining stars in the observable universe combined. And then, just as suddenly, the song changes. The newly formed larger black hole is distorted and unstable, like a water droplet that has just been struck by another. It quivers and vibrates, shedding its imperfections as more gravitational waves. This final phase is called the ring down. It sounds like the fading tone of a perfectly struck bell, a pure and simple note that quickly decays into silence. And then, there is nothing. The new black hole has settled into its perfect, quiet state, and its event horizon absorbs any further vibration. The song is over. This beautiful three-part song in spiral, merger, ring down has been heard again and again. Its shape is a perfect match for the predictions of our theories about black holes. It is a powerful and elegant confirmation of our understanding of gravity in its most extreme form. But for those searching for new physics, the key is to listen for a song that does not quite fit this perfect pattern. Part 9. The search for a different tune. 901,100 words. The search for Gravastars and other exotic compact objects is a search for a different tune in the universe's quiet hum. It is a quest to find a gravitational wave signal that contains a subtle but profound deviation from the perfect black hole song. As we have learned, the most promising signature to listen for is the sound of echoes. These echoes are the key difference we would expect from the merger of two objects with hard surfaces, like gravastars, instead of absorptive event horizons. Let us imagine again the merger of two gravastars. The in-spiral phase, as they orbit each other, would be identical to that of two black holes of the same mass. From this part of the song alone, we could not tell the difference. The merger itself would also be very similar, producing a massive burst of gravitational wave energy. But the final act, the ring down, is where the tune would change. Instead of a smooth, quickly fading tone that disappears into silence, the merger of two gravastars might produce a much more complex and extended final sound. The newly formed, larger gravastar would be vibrating violently. Because it has a hard surface, the powerful gravitational waves created in the merger wouldn't just radiate away. They would also be reflected. The region just outside the gravastar's surface can act like an echo chamber. Waves can get temporarily trapped, bouncing back and forth between the surface and the peak of the gravitational potential just a little further out. Each time a portion of these trapped waves escapes, it would send another, smaller pulse of gravitational waves out into the universe. To our detectors, this would sound like a series of echoes, each one fainter than the last, arriving at precise, regular intervals after the main merger event. The song would not end with a clean ring down into silence. It would end with a series of faint, dying whispers. The discovery of such a repeating, fading signal would be a profound moment in the history of science. It would be the first direct evidence that not all of the dark, compact objects in our universe are the black holes described by classical relativity. So, scientists are engaged in a meticulous and patient search. They are sifting through the data from every merger event they detect, looking for these faint, predicted echoes. They develop sophisticated computer algorithms to scan the noisy data, trying to pick out a repeating pattern in the moments after the main signal. It is like trying to hear a pin drop in the moments after a clap of thunder. It requires immense care, precision, and a deep understanding of what the signal should look like. The search is a quiet and persistent one, a testament to our desire to hear every note in the cosmic symphony. Part 9. A faint and distant possibility, 650-750 words. It is important, in our gentle journey of exploration, to be honest and clear about the current state of this search. As of now, despite the patient and careful listening by scientists around the world, no definitive evidence for gravastars, or for their gravitational wave echoes, has been found. Every single gravitational wave event that has been detected and analyzed has been beautifully and perfectly consistent with the theory of merging black holes. The in-spirals, the mergers, and the ring-downs all match the predictions of Einstein's theory of general relativity with remarkable precision. There have been a few tantalizing hints, a few moments in the noisy data where a small random fluctuation might look a little like an echo. But upon closer inspection, None of these have risen to the level of a true, statistically significant discovery. They are, for now, most likely just random noise, the normal static of the universe and our detectors. This lack of evidence is not a failure. It is, in itself, a piece of scientific information. It tells us that if gravastars do exist, they are either very rare, or their echo signal is even fainter and more difficult to detect than we have imagined. Or it may simply mean that the universe truly does prefer to make black holes, and that the elegant idea of the gravastar is just that, a beautiful idea that does not happen to be realized in our particular cosmos. Science is a process of asking questions and listening carefully for the answers. Sometimes, the universe answers with a clear and resounding yes. Other times, it answers with a quiet, persistent silence, and this silence is just as important. It guides our search, telling us where not to look, and refining our understanding of what is and is not possible. The search continues, with ever more sensitive detectors being planned and built. The possibility remains a faint and distant one, but the quest to listen for it continues to inspire and drive our exploration of the cosmos. Part 9. The Beauty of the Search, 750-900 words. So, as we conclude this chapter, let us reflect not on the results, but on the profound beauty of the search itself. The quest for gravastars, for echoes in the fabric of space-time, is a perfect example of the gentle, persistent, and hopeful nature of scientific inquiry. It is a story about human curiosity in its purest form. We are a species that looks up at the darkness and does not just accept it as a void. We fill it with questions. We build incredible instruments of breathtaking sensitivity, not for any immediate practical gain, but simply because we wish to understand. We spend years listening for a sound that may not even exist, driven by the quiet possibility that the universe might be even more wonderful and more strange than we have so far imagined. The beauty of this search lies in its patience. It is a slow and meditative process. It involves sifting through vast amounts of data with the careful attention of a monk tending a Zen garden. Every piece of noise must be understood and cleared away in the hope of revealing a single, faint, meaningful signal underneath. It is a testament to our ability to work together, across nations and generations, on a single, peaceful goal of expanding our cosmic awareness. And the beauty also lies in its honesty. Science is not afraid of the answer being no. If, after a century of listening, we find no evidence for gravastars, then that too is a form of knowledge. It will be a powerful confirmation of Einstein's original vision, a sign that the universe does indeed embrace the beautiful and paradoxical nature of the black hole. The goal is not to prove a particular idea right, but to get closer to the truth, whatever that truth may be. So, whether gravastars are real or are destined to remain a beautiful theoretical dream, the journey of searching for them enriches us. It pushes our technology to its limits. It deepens our understanding of gravity. And it reminds us that we live in a universe that is still full of profound and gentle mysteries. The search itself is a quiet act of wonder, a peaceful conversation we are having with the cosmos, listening with great care for its reply. Chapter 10. The Cosmic Family of Objects. Our journey has focused on the quiet contrast between black holes and gravastars. But to truly appreciate the richness of the cosmos, let us now broaden our view. Let us place the gravastar within a larger, more diverse family of theoretical objects, a whole spectrum of beautiful possibilities that might exist in the deepest, darkest corners of space. Part 10. A spectrum of possibilities, 650-750 words. For a long time, our picture of the final states of stars was quite simple. A small star like our Sun would end its life as a quiet, dense white dwarf. A more massive star would explode in a supernova, leaving behind an even denser neutron star. And a very massive star would collapse all the way into a black hole. For many years, these were the three known and accepted final chapters in a star's life story. But as our understanding of physics has deepened, particularly at the intersection of gravity and quantum mechanics, we have begun to imagine other possibilities. Theoretical physicists have realized that the universe might be more creative than we once thought. The transition from a neutron star to a black hole might not be a simple one-step process. There could be a whole spectrum of other objects that could exist in between, other stable configurations that matter and energy could adopt. The Gravastar is just one, albeit very elegant, member of this theoretical family. These other possibilities are often called black hole mimickers or exotic compact objects. They are all, by definition, objects that are incredibly dense and massive, with gravitational fields so strong that, from a distance, they would be almost impossible to distinguish from a black hole. But on the inside, they are all profoundly different, each one offering a unique, non-singular solution to the problem of gravitational collapse. Exploring this spectrum of possibilities is like being a cosmic botanist, discovering a whole new ecosystem of strange and wonderful plants. Each one has a different structure, a different reason for its stability. Each one represents a different way that the fundamental laws of nature could manifest themselves under the most extreme conditions. The universe may not have chosen just one answer, but many. Part 10. The Gentle Boson Stars, 750-900 words. Let us take a soft and gentle detour to meet another member of this cosmic family, the Boson Star. This is another beautiful theoretical object that offers a peaceful, non-singular alternative to a black hole. A boson star, as its name suggests, would be a star made up entirely of a type of fundamental particle called a boson. In the quantum world, particles come in two main families, fermions and bosons. Fermions are the particles of matter, like the electrons, protons, and neutrons that make up you and me. Fermions are famously antisocial. They obey a rule called the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state at the same time. It is this principle that creates the electron degeneracy pressure that holds up a white dwarf star, and the neutron degeneracy pressure that holds up a neutron star. They resist being squeezed together. Bosons, on the other hand, are the particles of force and energy, like the photons that make up light. Bosons are famously social. They have no problem with being in the same state at the same time. In fact, they prefer it. You can pack an unlimited number of bosons into the same space, and they will begin to act in concert as a single, coherent quantum wave. A boson star is a hypothetical object made from a cloud of these social boson particles. If a stable, massive boson exists in nature, something like the hypothetical axion, a candidate for dark matter, then it's possible that a huge number of them could gather together under their own gravity. They would not form a hard, dense object like a neutron star. Instead, they would settle into a collective quantum state, a Bose-Einstein condensate of galactic proportions. The resulting object would be a strange, transparent ghost star. It would have immense mass and gravity, but you could, in principle, pass right through it, interacting only with its gravitational field. A boson star is held up against collapse, not by a familiar pressure, but by a quantum mechanical effect related to the uncertainty principle. It is a delicate, fuzzy, and entirely non-singular object, another testament to the creative and gentle ways the universe might choose to build its most massive and compact structures. Part 10. Comparing architectures, 750-900 words. Let us now gently compare the internal architectures of these three incredible objects, the black hole, the Gravastar, and the boson star. This comparison should not be seen as a competition to see which one is better, but as an appreciation of the different artistic styles of the cosmos, the different ways the laws of physics can build a final home for matter and energy. First, we have the black hole, the masterpiece of classical general relativity. Its architecture is one of profound and simple emptiness. It has an event horizon, a boundary of no return, and at its heart, a singularity, a point where the architecture itself dissolves into an infinite question. It is a structure defined by what it is not. It is a hole in space-time, a region of pure, inescapable gravitational collapse. Its beauty is the stark, minimalist beauty of a perfect void. Next, we have the Gravastar, the masterpiece of quantum gravity engineering. Its architecture is one of layered, balanced perfection. It is a three-part structure, a dense outer shell of exotic matter, an empty, repulsive de Sitter core, and an energetic membrane holding the two in harmony. It has no singularity and no event horizon, but a hard physical surface. It is a structure of perfect equilibrium, a cosmic monument built to last for eternity. Its beauty is the intricate, harmonious beauty of a perfectly designed machine. Finally, we have the boson star, the masterpiece of collective quantum mechanics. Its architecture is one of a single, unified and ethereal substance. It is a vast, transparent cloud of particles, all acting as a single quantum wave. It has no hard surface, no distinct layers, just a fuzzy, ghost-like presence. It is held up against gravity by the gentle, fundamental uncertainty of the quantum world. Its beauty is the subtle, shimmering beauty of a ghost, a structure that is barely there at all, and yet possesses immense gravitational power. Each of these objects tells a different story about the ultimate nature of gravity and existence. The black hole tells a story of surrender. The Gravastar tells a story of balance. The boson star tells a story of gentle quantum resistance. The universe could contain all three, each one a different final verse in the poem of a star's life. Part 10. A universe of rich variety, 750-900 words. Let us now contemplate what it would mean to live in a universe that contains such a rich variety of compact objects. For so long, the dark, massive things in the cosmos were all painted with the same brush, all called black holes. But what if the reality is more diverse, more colorful, and more wondrous? What if the cosmic darkness is not uniform, but is filled with a whole family of different species of object? Imagine being an explorer in a newly discovered land. At first, all the trees might look the same. But as you look closer, you begin to see the subtle differences. The shape of the leaves, the texture of the bark, the way they catch the light. You realize you are not in a forest, but in a rich and diverse ecosystem. The search for exotic compact objects is like this. We are learning to look closer at the dark trees of the universe and to appreciate their potential diversity. A universe with such variety would be a more interesting place. It would mean that the laws of physics have not just one, but multiple ways of solving the problem of gravitational collapse. It would be a testament to the universe's creativity and flexibility. It would provide physicists with a natural laboratory for studying the interplay of gravity and quantum mechanics in ways we could never hope to replicate on Earth. Each different type of object would be a new clue, a new piece of the puzzle of a final, unified theory. This richness would also add a layer of beautiful complexity to the story of the cosmos. The evolution of galaxies, the dynamics of star clusters, the background hum of gravitational waves. All of these things would be subtly different in a universe populated by a diverse family of compact objects, compared to a universe with only black holes. The story of the universe would have more characters, more plot twists, and a more satisfyingly intricate narrative. To embrace this possibility is to embrace a sense of humility and wonder. It is to admit that our current picture is likely incomplete, and to be open to the possibility that the universe is grander and more varied than our theories have yet fully captured. It paints a picture of a cosmos that is not stark and simple, but is teeming with a rich variety of forms, each one a unique and beautiful expression of the fundamental laws of nature. Part 10a. The unifying thread of gravity, 901,100 words. Amidst all this wonderful theoretical diversity, the black holes, the Gravastars, the boson stars, and other possibilities we have not even named it, is easy to feel a little lost. But there is a single, unifying thread that runs through this entire cosmic family, a gentle and powerful force that tells all of their stories. That thread is gravity. Each one of these objects, no matter how different its internal architecture, is first and foremost a creature of gravity. They are all born from gravitational collapse, the process by which a massive object's own gravity becomes too strong for any other force to resist. They all exist as deep, quiet wells in the fabric of space-time, their immense mass bending the paths of nearby light and matter. From a great distance, they are all masters of their gravitational domain, holding galaxies together and dictating the cosmic dance of stars and gas. Gravity is the great sculptor of the universe on its largest scales, and these compact objects are its ultimate masterpieces. They are what happens when gravity is allowed to work, almost unopposed, on a huge collection of matter. The differences between them arise from the other, more subtle forces of nature that come into play at the very last moment, to try and halt the final, complete collapse. For a black hole, no other force is successful, and gravity wins completely, leading to an event horizon and a singularity. The black hole is the story of pure, triumphant gravity, as described by Einstein. For a gravastar, a new force, born from a quantum phase transition of spacetime itself, rises up at the last second to meet gravity in a state of perfect, eternal balance. The gravastar is the story of gravity held in a perfect, harmonious stalemate. For a boson star, the gentle collective quantum nature of its constituent particles provides a soft, continuous resistance that prevents gravity from ever reaching a point of collapse. The boson star is the story of gravity being tamed by the strange and subtle rules of the quantum world. Each object is a different dialogue with gravity. They are different answers to the same cosmic question. What happens when you gather a huge amount of mass in one place? The unifying thread is the question itself, the question posed by gravity. The diversity of the answers is what makes the universe so rich. But they are all part of the same story, the grand and unfolding narrative of gravity's role in shaping the quiet darkness between the stars. Understanding gravity, in all its depth and subtlety, is the key to understanding this entire beautiful family of cosmic objects. Chapter 11. A matter of perspective. Having placed the gravastar within a family of possibilities, let us now consider a crucial question. How would these objects actually appear to us? How could we tell them apart? The differences, it turns out, are incredibly subtle, a quiet matter of perspective that would require us to look at the universe with more precision and care than ever before. Part 11. The view from afar, 750-900 words. Let us begin our observation from a great and safe distance. Imagine we are in a spaceship, many light years away, observing a dark, massive object at the center of a star cluster. From this vantage point, what would we see? The answer, for a black hole, a gravastar, or a boson star of the same mass, is that we would see almost exactly the same thing. The dominant feature of these objects, from a distance, is their immense gravitational field. And according to a classic theorem of physics, the gravitational field outside a spherical, non-rotating object depends only on its total mass, not on what it is made of on the inside. This means that the way these objects bend the light of distant stars, a phenomenon known as gravitational lensing, would be identical. The stars in orbit around them would follow the exact same elliptical paths, at the exact same speeds. We could carefully measure the orbits of these stars over many years. From these orbits, we could calculate the mass of the central object and the volume of space it is contained within. We would find, in all three cases, that we have an enormous amount of mass packed into an incredibly small region of space, a region so dense that no known form of conventional matter could support itself against collapse. This is, in fact, how we first discovered the supermassive black hole at the center of our own galaxy. We saw the stars, but we could not see what they were orbiting. So, from afar, our observations would confirm that we are looking at an incredibly massive, compact object. But these observations alone could not tell us what is happening at the very edge of that object. They cannot tell us if there is an event horizon, a hard surface, or a fuzzy, transparent cloud. The grand gravitational signatures are the same. The differences are hidden in the fine details, in the subtle clues that would only be revealed if we could get much, much closer, or if we could observe an event, like a merger, that directly probes the object's very edge. The view from afar shows us the family resemblance, but to see the individual faces, we need a different perspective. Part 11. The shadow in the light, 750-900 words. In 2019, humanity achieved a remarkable feat. using a network of radio telescopes spread across the entire globe. Acting as a single, Earth-sized observatory, the Event Horizon Telescope collaboration captured the first-ever direct image of a black hole's silhouette. We saw the shadow of the supermassive object at the heart of the galaxy MATE-7. This image was not of the black hole itself, but of the glowing, superheated gas swirling around it, with a dark circle at its center. This dark circle is the black hole's shadow. This shadow is created by the black hole's intense gravity. It is a region of darkness cast upon the bright background of the accretion disk. The shadow is larger than the event horizon itself, its size determined by the black hole's photon sphere, the last stable orbit for light. Any light that enters this region is destined to be captured by the black hole. The image was a beautiful confirmation of Einstein's theories, the size and shape of the shadow matching the predictions perfectly. Now let us ask a gentle but critical question. What would this image look like if the object at the center of MATE-7 were not a black hole, but a gravastar? The surprising answer is that it would look almost identical. A gravastar of the same mass would have a very similar photon sphere, the region where light can orbit. Therefore, it would bend the light from the accretion disk behind it in a very similar way, creating a shadow of nearly the same size and shape. To our current telescopes, the image of a black hole's shadow and the image of a gravastar's shadow would likely be indistinguishable. Both would appear as a dark circle, surrounded by a bright ring of light. The grand visual signature is, once again, the same. This highlights the incredible challenge of telling these objects apart. They are masters of disguise, their internal differences hidden behind the overwhelming and universal effects of their powerful gravity. Seeing the shadow is a monumental achievement, but to see the true nature of the object casting it, we must look for even more subtle clues, for faint differences in the light that comes from the very edge of the darkness. Part 11. Subtle differences in the glow. 901,100 words. The key to distinguishing these cosmic objects might lie not in the shadow they cast, but in the subtle qualities of the light that surrounds them. The differences would be faint, requiring a level of precision in our observations that we are only just beginning to achieve. But in these subtle differences in the glow, the true nature of the object might be revealed. Let us first consider the accretion disk, the swirling disk of hot gas that orbits the central object. For a black hole, this disk is thought to extend all the way down to the innermost stable circular orbit, the last place where matter can circle peacefully before making its final one-way plunge across the event horizon. The gas in this inner region is incredibly hot, moving at nearly the speed of light, and it glows with a specific and predictable spectrum of light. Now, consider a gravastar with its hard surface. An accretion disk could still form around it, but the inner edge of that disk would be different. It would not end at an empty orbit, but would presumably interact with the gravastar's surface. This interaction could heat the gas in a different way, producing a slightly different temperature profile, a different spectrum of light. Perhaps the gas would pile up against the surface, creating a bright hot spot that is not present in the black hole model. These are the kinds of subtle spectral signatures that astronomers could look for. Another potential difference lies in the light, or lack thereof, coming from the central object itself. A black hole, by definition, does not have a surface that can emit light. The shadow should be perfectly black. A gravastar, on the other hand, does have a surface. While this surface would be incredibly cold and dim, it might not be perfectly black. Quantum processes, or the very slow absorption of matter, might cause it to have a very faint residual glow. This glow would be incredibly redshifted by the intense gravity, but it might be detectable as a faint radio signal coming from the center of the shadow. Finding such a signal, a faint warmth where there should be absolute cold, would be a revolutionary discovery. Furthermore, some models of exotic compact objects suggest they might have weak magnetic fields, something a classical black hole should not possess. These magnetic fields could interact with the surrounding plasma, creating unique patterns of polarized light in the glowing ring. Measuring the polarization of the light around the shadow, as the Event Horizon Telescope has begun to do, could reveal these subtle magnetic fingerprints. Each of these clues, a change in the spectrum, a faint glow from the surface, a twist in the polarization, is a quiet whisper from the edge, a subtle difference in the glow that could, one day, allow us to tell these cosmic cousins apart. Part 11. A question of time, 650-750 words. Finally, let us consider a subtle difference that is invisible to the eye, but is profound in its implications. The different ways that time flows at the edge of these objects. This is a matter of perspective that gets to the very heart of what makes them different. As we have learned, at the event horizon of a black hole, the phenomenon of gravitational time dilation becomes infinite. From the perspective of a distant observer, time for an object falling onto the black hole slows down and comes to a complete stop at the horizon. A clock falling in would appear to tick slower and slower, its final tick taking an eternity to reach us. The event horizon is a boundary of infinite time. Now, let us consider the hard surface of a gravastar. This surface exists just outside where the event horizon would have been. Here, the gravitational time dilation is immense, but it is not infinite. Time at the surface of a gravastar would run incredibly slowly compared to our time, perhaps billions or trillions of times slower. But it would not be frozen. A clock on the surface would still, however slowly, tick. This is a subtle, but absolute, distinction. A black hole represents a true boundary of time. A gravastar represents a place where time is stretched to its limit, but does not break. This difference might have observable consequences. For example, in the gravitational wave echoes we discussed earlier, the time delay between the echoes would be directly related to the travel time for the waves bouncing near the surface. This time delay is a measurement of the nature of time in that extreme environment. If we were ever to detect these echoes and measure the time between them, we would not just be proving the existence of a hard surface. We would be taking a direct measurement of the flow of time at the very edge of the void. We would be probing the structure of space-time in a way that is impossible with a black hole. This question of time, of whether it stops completely or just slows down to a near-perfect standstill, is one of the most gentle, yet most profound, ways to distinguish between these silent, massive inhabitants of the cosmic darkness. Chapter 12. The Philosophical Silence. Our journey has taken us through the physics, the structure, and the potential observations of gravastars. For our final chapters, let us drift into a more gentle and reflective space. Let us contemplate the quiet, philosophical appeal of these theoretical objects, and what they might tell us about our own place in the grand, silent story of the cosmos. Part 12. A universe without singularities, 750-900 words. Let us begin by contemplating the philosophical comfort of imagining a universe that does not contain singularities. The singularity at the heart of a black hole is a profound and unsettling concept. It is a point where the laws of physics, our language for describing the universe, fall silent. It is a place of infinite density and infinite space-time curvature. It is a true infinity existing within our physical cosmos, a loose thread in the otherwise elegant tapestry of general relativity. For many scientists and philosophers, these infinities are a sign of an incomplete theory. They feel intuitively that nature should not contain such points of perfect breakdown. The universe, in all its other manifestations, appears to be finite, ordered, and understandable. Why should it permit these small pockets of absolute unknowability? The singularity is a kind of cosmic edge, a cliff off which our understanding must fall. The Gravastar model offers a gentle and beautiful alternative. It proposes a universe that is everywhere whole and understandable. By halting the process of gravitational collapse just before a singularity can form, it heals this wound in our physical theories. It replaces the infinite, paradoxical point with a smooth, finite and physical structure. The de Sitter core of a gravastar is a place of extreme physics, to be sure, but it is a place that our laws can, in principle, describe. It is a region of space-time, not a breakdown of space-time. To imagine a universe without singularities is to imagine a cosmos that is more complete, more harmonious, and ultimately, more knowable. It suggests that there are no truly sealed-off rooms in the cosmic house. no places where the rules simply cease to apply. It means that the universe is governed by a single, unified set of laws that work everywhere, from the gentle fall of a leaf on Earth to the very heart of the most massive object in the galaxy. This is a deeply appealing and philosophically peaceful vision. It is a vision of a rational and elegant cosmos, a universe that does not resort to infinities to solve its problems. It is a quiet affirmation that with enough patience and gentle thought, every corner of existence may one day be open to our quiet, peaceful understanding. Part 12. The Conservation of Story. 750-900 words. Let us now revisit the information paradox, but from a more poetic and philosophical perspective. The idea that information could be destroyed in a black hole is unsettling not just for physicists, but for our intuitive sense of how the world works. We feel that things should not be able to truly vanish without a trace. The universe, we feel, should have a perfect memory. The conservation of information is, in a sense, the conservation of story. Every particle, every star, every living being has a unique story, a unique configuration of properties that defines it. The idea that these stories could be completely and utterly erased from the cosmic record feels like a profound loss. It suggests a universe that is forgetful, a universe where the past can be truly and permanently disconnected from the future. The Gravastar offers a gentle and deeply satisfying resolution to this philosophical unease. In the Gravastar model, stories are never lost. When matter falls onto the Gravastar's surface, its information is not destroyed. It is preserved, encoded onto the physical substance of the shell. The Gravastar becomes an archive, a library of all the stories it has encountered. This is a vision of a universe with a perfect and incorruptible memory. It is a cosmos where every event, no matter how small, leaves a permanent mark on the fabric of existence. The stories are not erased. They are simply added to a new, larger chapter of the Gravastar's eternal story. This is a profoundly optimistic and reassuring vision. It suggests a universe that is, at its core, a just and reliable storyteller. It does not allow for the arbitrary destruction of its own history. To contemplate this is to feel a sense of deep cosmic peace. It is the peace of knowing that you are part of a grand, unbroken narrative. The story of the universe is a single, continuous thread, stretching from the Big Bang to this very moment and on into the distant future. The Gravastar, in this philosophical light, is a guardian of that thread. It is a silent, eternal librarian, ensuring that no page of the cosmic book is ever torn out. It is a testament to a universe where every story matters, and every story, in some form, is preserved for all of time. Let us now float in a gentle meditation on the very nature of our journey tonight. The conversation we have been having, the gentle debate between the black hole and the Gravastar, is a perfect illustration of how science works at the very edge of human knowledge. It is a process that is often misunderstood as a series of harsh arguments and dramatic breakthroughs. But at its heart, it is a quiet, patient, and deeply creative act of wonder. The edge of knowledge is not a battlefield where theories fight to the death. It is a calm and misty shore, where we stand looking out at a vast, unknown ocean. From this shore, we send out small, beautiful boats of thought. These boats are our theories, our new ideas. The Gravastar is one such boat, exquisitely crafted from the language of mathematics and a deep intuition about how the universe ought to be. It is a vessel built not to conquer the ocean, but to explore it, to see if it can sail without sinking. The tools we use to build these boats are imagination and logic, working in perfect harmony. Physicists like Mazur and Mottola did not discover the Gravastar with a telescope. They discovered it with a pencil and paper, by following the elegant rules of physics to their logical and sometimes surprising conclusions. They imagined a new possibility, the phase transition of space-time, and then gently explored where that single beautiful idea would lead. This is the creative heart of science. It is the ability to dream of a different kind of universe, and then to build that dream with mathematical precision to see if it holds together. Once a new boat is launched, the second part of the process begins, the patient act of listening. We turn our instruments, our gravitational wave detectors, our planet-sized telescopes towards the ocean, and we listen for a sign. We listen for the echoes, for the subtle differences in the glow, for any whisper from the cosmos that might tell us that this new boat has found a real shore on the other side. This part of the journey requires immense patience. The universe does not give up its secrets easily. The answers may take a lifetime of quiet listening to emerge. This entire process is one of profound humility. It is an admission that our current maps are incomplete. It is an acknowledgement that the ocean of our ignorance is vast, and our island of knowledge is small. But it is also an act of profound hope. It is the belief that by launching our little boats of thought, by listening with great care and stillness, we can, slowly, gently, expand the shoreline of our understanding. The debate between black holes and gravastars, then, is not a conflict. It is a beautiful and necessary part of this process. It is a sign of a healthy and vibrant exploration. It is the universe being so rich and so wondrous that it can support more than one beautiful idea at the same time. We can hold both possibilities in our minds, the elegant void of the black hole and the balanced monument of the gravastar, and appreciate them both as magnificent testaments to the power of human thought to grapple with the deepest, most silent mysteries of existence. As we embrace this gentle, exploratory nature of science, let us find peace in the fact that the gravastar remains, for now, unseen and unproven. There is a quiet beauty in a purely theoretical idea, a kind of perfection that can exist in our minds before it is tested against the messy reality of the cosmos. A theory, before it is proven, is a form of poetry. It is a story we tell about the universe, a narrative written in the language of mathematics that is valued for its elegance, its internal consistency, and the beautiful new perspective it provides. The Gravastar is a magnificent poem. It is a story of balance, harmony, and eternal preservation. It solves paradoxes with an elegant twist, and it paints a picture of a cosmos that feels whole and complete. The value of this poem does not depend entirely on whether or not we find a physical gravastar out there in the darkness. The value of the idea lies in the journey it has inspired. The concept of the gravastar has forced physicists to think more deeply about the nature of gravitational collapse. It has inspired new ways of looking for observational signatures. It has pushed our understanding of both general relativity and quantum mechanics into new and fertile territory. Even if it turns out that our universe does not make gravastars, the thought experiment of the gravastar will have served a profound purpose. It will have helped us to better understand the alternative, to better appreciate the beautiful strangeness of the black hole. Sometimes, we must imagine what is not real in order to fully grasp what is. So let us hold the idea of the gravastar in our minds without the need for immediate, concrete proof. Let us appreciate it as a beautiful piece of intellectual art, a testament to the creative power of the human mind. There is a deep and quiet peace to be found in the realm of pure possibility, in the gentle contemplation of the unseen and the unproven. As we come to the end of this philosophical contemplation, let us perform a final, gentle thought experiment. There is no need to answer, no need to even think too actively. Simply allow your mind to feel the texture of two different possible universes, and notice which one feels more peaceful, more resonant to you in this quiet moment. First, imagine a universe where the final word on stellar collapse is the black hole. This is a universe of profound and beautiful voids. It is a cosmos that embraces the paradoxical, that contains points of infinite mystery where our knowledge must come to a respectful end. It is a universe where stories can, perhaps, be temporarily lost, hidden behind a one-way door from which no message can return. This universe has a stark, minimalist elegance. It is a cosmos of deep and perhaps permanently unknowable secrets, a place of majestic and absolute surrender to the power of gravity. Feel the quiet wonder of this universe, with its silent, hungry voids and its gentle, fading glow of Hawking radiation. Now, let us imagine a different universe, a universe where the final word is the gravastar. This is a universe of perfect and eternal monuments. It is a cosmos that favors balance and order, a place where the laws of physics are everywhere whole and understandable, with no infinities or paradoxes. It is a universe where every story is meticulously preserved, where nothing is ever truly lost, but is instead archived in a permanent, unchanging library. This universe has an intricate, harmonious elegance. It is a cosmos that is, in principle, completely knowable, a place of profound stability and eternal preservation. Feel the quiet peace of this universe, with its silent, balanced monuments and its perfect, unchanging forms. There is no right or wrong answer here. Both visions of the cosmos are beautiful. Both are born from the same set of physical laws, interpreted in a different, gentle light. The universe we inhabit may be one of these, or the other, or a mixture of both. But as you drift now, on the edge of sleep, you can allow your mind to rest in the version that brings you the most comfort, the most sense of peace, the most profound feeling of being at home in the grand, silent mystery. Our long journey of thought is now drawing to a close. We have traveled to the theoretical edge of the cosmos, to the very heart of the deepest gravitational wells. Now, it is time to slowly, gently, drift back, carrying the quiet wonder of our exploration with us, as we return to the familiar stillness of our own small corner of the universe. Let your awareness begin its gentle journey homeward. We pull back from the hard surface of the Gravastar, from the edge of the void where time itself almost stands still. We drift away from the silent cosmic monuments, letting them recede back into the velvet darkness, their perfect forms holding their eternal watch. We leave behind the subtle glow of accretion disks and the faint theoretical hum of gravitational wave echoes. Our journey has been a long one, a flight of the imagination into the deepest realms of physics and philosophy. We have held in our minds the profound riddle of the singularity, the gentle paradox of a lost story. We have witnessed the birth of a new and elegant idea, an alternative born from a quiet question and a deep desire for harmony. We have explored, layer by layer, a structure of perfect balance, a symphony of forces playing out in eternal, silent peace. As we drift back, let us not feel the need to hold on to every detail. Let the specific concepts soften and blur. Let the names and the numbers fade away. What we carry with us is not a collection of facts, but a feeling. It is the feeling of a universe that is richer, stranger, and more wonderfully creative than we often imagine. It is the feeling of quiet wonder that comes from contemplating the grandest and most gentle of mysteries. Let this feeling be a soft, warm blanket for your mind. You have traveled far, and now you are returning. The journey is complete. The exploration is done for tonight. All that is left is to float peacefully in the afterglow of this cosmic story, as our awareness drifts slowly, slowly back from the far edges of the universe. As our awareness continues its gentle return, let it settle closer to home. Let it come to rest on the familiar image of the night sky, as seen from our own planet, Earth. Perhaps you can see it through your window, or perhaps you can just picture it in your mind. A dark canvas, sprinkled with 1,000 distant points of light. Each one of those lights is a star, a sun, much like our own. Each one is a vast sphere of hot gas, held in the same delicate balance between gravity and pressure that we have been exploring on a much grander scale. Each star is living out its own life story, a narrative written in the language of nuclear fusion that unfolds over millions or billions of years. And each star has a destiny. The smaller ones will one day fade into gentle, glowing embers called white dwarfs. But the largest and most brilliant of those stars, the bright blue giants that shine with such intensity, are destined for a more dramatic end. They are the stars that will one day undergo the kind of gravitational collapse we have been contemplating tonight. To look up at the night sky is to look at a field of possibilities. Some of those distant twinkling lights may one day, in a future so distant it is beyond our comprehension, become black holes. Others, if the universe allows for it, may become the silent, eternal monuments we have called Gravastars. The great cosmic drama we have been exploring is not an abstract fantasy. It is the real, and very quiet, future of the brightest stars in our own sky. And the very same laws of physics that will guide their final moments are the laws that are at work right here, right now, in this very room. The gentle force of gravity that is holding you comfortably in your bed is the same force that, in its most extreme form, creates these incredible cosmic objects. We are not separate from this story. We are a part of it, woven from the same stardust and governed by the same deep cosmic harmonies. As we lie here, under these familiar stars, let us embrace the ever-present mystery they represent. Our journey tonight has been a quest for answers, an exploration of different theories that try to explain the deepest secrets of the cosmos. But the true beauty of our relationship with the universe is not found in having all the answers. It is found in the quiet, peaceful presence of the questions themselves. Does the universe create singularities, or does it always find a way to create order? Are the stories of the cosmos ever truly lost, or are they always preserved? Are those distant, dark objects holes in space-time, or are they perfect, eternal monuments? For now, we do not know the final answer. And there is a profound peace to be found in that not knowing. To live with mystery is to live in a state of perpetual wonder. It is to know that the universe is always larger than our current understanding of it. It is to know that there are always new shores to explore, new ideas to contemplate, new and more beautiful questions to ask. Answering a question brings a momentary satisfaction, but a great and gentle mystery can be a companion for a lifetime. The question of Gravastars is one such companion. It is a quiet reminder that we should hold our theories lightly, that we should always be open to the possibility that the universe has imagined something even more elegant and harmonious than we have. It is an invitation to remain curious, to keep listening, and to be comfortable with the vast, silent spaces in our knowledge. So let us not feel any need to resolve this mystery tonight. Let us simply allow it to be. Let the question hang in the air, as gentle and as beautiful as the distant stars themselves. We can rest peacefully in the embrace of this beautiful uncertainty, knowing that the universe's capacity for wonder is truly infinite. As our journey comes to its final resting point, let us gather the threads of our exploration into one last, gentle tapestry. Let us see the entire story we have traversed tonight, not as a series of separate ideas, but as a single, unfolding narrative, a story that the universe is writing in the very fabric of space-time. Our story began in a familiar place, with the classical black hole. This was the first chapter, a tale of pure, triumphant gravity, a simple and powerful story of a collapse that could not be stopped. It was a beautiful story, but it left us with two gentle riddles, a final page that dissolved into the infinity of a singularity, and a library of cosmic stories that seemed to be lost forever. These quiet puzzles, these gentle inconsistencies, were the motivation for the second chapter of our story. This was a tale of human curiosity, of the patient search for a more harmonious narrative. It was the story of scientists listening carefully to the whispers of the universe and daring to imagine a different kind of ending. This chapter was about the birth of a new idea, the quiet genesis of the Gravastar. The third and longest chapter of our story was the exploration of this new idea. We journeyed through the architecture of this theoretical object, a cosmic monument built in three harmonious parts. We visited the dense outer shell, a guardian of stillness. We floated in the empty, expansive de Sitter core, the silent engine of stability. And we marveled at the infinitesimally thin layer between them, the conductor of a perfect symphony of physics. This was a story of balance, of preservation, and of an eternal, unchanging peace. Finally, our story broadened its perspective. We placed the Gravastar in a family of other cosmic possibilities, and we contemplated the subtle clues and quiet echoes we might one day use to read this chapter of the cosmic book. We drifted into a philosophical silence, feeling the different textures of a universe with voids versus a universe with monuments. All of this, from the paradox to the solution, from the collapse to the balance, is a single grand story. It is the story of gravity, energy, and the deep quantum nature of reality. It is a story written not in words, but in the language of mathematics, in the curvature of space-time, and in the destiny of stars. And we, in our quiet moments of wonder, have the profound privilege of being its readers. And so, we arrive at the final moment of our main narration. We have traveled far and wide in our minds, and now we are back, resting in the quiet comfort of our beds. Let this final thought be the bridge that carries you gently into sleep. The entire journey tonight, the deep questions and the elegant possibilities, can be summarized in a single, peaceful feeling. The peace of not knowing. All day long, our minds are busy. They are engaged in knowing, in solving, in planning, in remembering. We feel a constant pressure to have the answers, to be in control. But as night falls, we are given a gentle invitation to let all of that go. Sleep is an act of surrender, a release of the need to know, a peaceful trust in the quiet darkness. The mysteries of the cosmos offer us a beautiful way to practice this gentle art of surrender. We have asked the deepest questions tonight. What is at the heart of a collapsed star? Where do the stories of the universe go? We have explored a possible answer in the Gravastar, a beautiful and comforting idea. But we do not need to hold on to it. We do not need to solve the puzzle. The act of asking the question, of opening our minds to the wonder, is enough. Let the story of the Gravastar be a gentle lullaby for your mind. Let the image of a perfectly balanced, silent, and eternal monument be a symbol of the deep peace that you can now allow yourself to feel. You can release the day. You can release the need to understand. You can simply float, like a tiny spaceship in the vast, quiet sea of the night, in the beautiful, endless possibility of the cosmos. Find peace, now, in the gentle act of not knowing, and allow yourself to drift. Tonight, we have journeyed together from the beautiful paradox of the black hole to the serene harmony of the Gravastar. We have replaced a story of an endless fall with a story of a perfect, eternal balance. In the deepest, most silent corners of the cosmos, the universe may be crafting structures of unimaginable peace. Let this thought be a comfort to you now. You have traveled far in your mind, and you have contemplated wonders. Now, your journey is over. It is time to rest. You have permission to let go of my voice, to let go of these thoughts, and to embrace the quiet stillness of sleep. May your dreams be as peaceful as the silent, balanced dark between the stars. Sleep well. What other cosmic mysteries bring you a sense of gentle wonder and peace? Feel free to share your thoughts in the comments when you awaken. Thank you for joining me on this quiet journey. If you found a moment of rest, a simple like and subscription helps our channel create more peaceful explorations for others to find. The universe is filled with silent wonders, waiting patiently for our return. When you are ready for another story, our collection of cosmic journeys is here for you. For now, simply rest.